The universe operates on rules that seem to defy common sense. At the smallest scales of reality, the laws of physics transform into something strange and wonderful. Tonight, we explore the fundamental principles of quantum mechanics, the science that describes the behavior of the tiniest building blocks of existence. Let us begin with a concept that challenges everything we think we know about the nature of reality itself. Wave-particle duality reveals that everything in the universe possesses two seemingly contradictory natures simultaneously. An electron, that tiny particle orbiting the nucleus of an atom, is both a discrete point in space and a spread-out wave of probability. You yourself, as you lie here listening, are also both particle and wave, though your wave nature is so incredibly small that it has no practical effect on your daily experience. Imagine dropping a pebble into a still pond. Ripples spread outward in circular waves, carrying energy across the water's surface. Now imagine that same pebble existing as a single point, a particle with definite mass and location. In the quantum world, these two descriptions are not alternatives, but simultaneous truths. Light behaves as both an electromagnetic wave spreading through space and as discrete packets of energy called photons. An electron spreads out like a wave when traveling through space, yet strikes a detector at a single point like a particle. The larger an object becomes, the shorter its associated wavelength grows, until it becomes utterly negligible. A baseball has a wavelength billions of times smaller than an atomic nucleus. For anything larger than molecules, the wave nature becomes impossible to detect or measure. But at the atomic scale, this dual nature dominates everything. It determines how atoms bond together, how electrons arrange themselves around nuclei, how light interacts with matter itself. This leads us to the strange realm of quantum superposition. In the world we experience every day, things exist in definite states. A coin is either heads or tails. A light switch is either on or off. A cat is either alive or dead. But in the quantum realm, particles exist in multiple states simultaneously until the moment they are observed or measured. Consider an electron orbiting an atomic nucleus. Before we measure its position, it does not exist at any single location. Instead, it exists as a cloud of probability, simultaneously present in many places at once. Only when we perform a measurement does the electron choose, in a sense, where to appear. Before measurement, it occupies a superposition of all possible positions. After measurement, it manifests at one specific location. This is not simply a limitation of our knowledge or measurement tools. The electron genuinely does not have a definite position before measurement. It exists in a state that is fundamentally different from anything in our everyday experience. A quantum bit, or qubit, in a quantum computer can be both 0 and 1 simultaneously, allowing these machines to perform certain calculations exponentially faster than classical computers. The famous thought experiment known as Schrödinger's cat illustrates this strangeness. A cat is placed in a sealed box with a quantum device that has a 50% chance of releasing poison. Until we open the box and observe the outcome, the quantum system exists in superposition. By extension, the cat itself exists in a superposition of alive and dead states. Only upon observation does reality choose one outcome over the other. Of course, this is a thought experiment meant to highlight the philosophical implications of quantum mechanics, not a real scenario involving an actual cat. Now we arrive at one of the most fundamental limitations built into the fabric of reality itself. The Heisenberg uncertainty principle states that certain pairs of properties cannot both be known with perfect precision simultaneously. The most famous example involves position and momentum. The more precisely you determine where a particle is located, the less precisely you can know how fast it is moving and in what direction. The more precisely you measure its momentum, the less precisely you can determine its position. This is not a statement about the limitations of our measuring instruments. It is a fundamental property of nature itself. A particle does not have both a definite position and a definite momentum at the same time. The act of measuring one property fundamentally disturbs the other. If you try to measure an electron's position very precisely, you must use light with a very short wavelength. But short-wavelength light carries high energy, which kicks the electron and changes its momentum in an unpredictable way. The uncertainty principle extends beyond position and momentum. It also applies to energy and time. You cannot know both the exact energy of a quantum state and the exact duration of that state with unlimited precision. This fundamental fuzziness at the quantum level has profound implications. It means that at the smallest scales, the universe is inherently probabilistic rather than deterministic. We can predict the probability of various outcomes, but we cannot predict with certainty what will happen in any individual quantum event. Perhaps the most mysterious phenomenon in quantum mechanics is quantum entanglement. When two particles interact in certain ways, they can become entangled, meaning their quantum states become correlated in a way that has no classical equivalent. Once entangled, measuring a property of one particle instantaneously affects the state of the other particle, regardless of the distance separating them. Einstein famously objected to this phenomenon, calling it spooky action at a distance. He believed that quantum mechanics must be incomplete, that there must be hidden variables determining the outcomes in advance. But decades of experiments have confirmed that entanglement is real. If you create two entangled photons and send them in opposite directions, measuring the polarization of one instantly determines the polarization of the other, even if they are separated by kilometers or light years. This does not allow faster than light communication. You cannot control what result you get when you measure your photon, so you cannot send information this way. But the correlation between the measurements is real and instantaneous. The two particles remain connected in a way that transcends space, as if they are parts of a single quantum system, no matter how far apart they travel. Entanglement is not just a curiosity for physicists. It forms the basis for emerging technologies like quantum cryptography, which uses entangled photons to create unbreakable encryption codes. If anyone tries to intercept and measure the photons, the entanglement is destroyed, alerting both parties that their communication has been compromised. Quantum computers also rely on entanglement to perform calculations that would be impossible for classical computers. Now let us explore quantum tunneling, a phenomenon that allows particles to pass through barriers that should be impenetrable according to classical physics. Imagine throwing a ball at a wall. If the ball does not have enough energy to break through or climb over the wall, it bounces back. But in the quantum realm, particles can sometimes appear on the other side of an energy barrier without having enough energy to surmount it, as if they simply walked through like a ghost. This happens because particles also behave as waves, and waves can extend into regions where classical particles cannot go. There is always a small but non-zero probability that a particle will be found on the far side of a barrier. For large barriers or large particles, this probability is vanishingly small. But at the atomic scale with thin barriers, tunneling happens regularly. Quantum tunneling is essential for nuclear fusion in the Sun and other stars. The nuclei of hydrogen atoms are positively charged and repel each other with tremendous force. They must get extremely close together to fuse into helium, releasing vast amounts of energy in the process. At the temperatures in the Sun's core, hydrogen nuclei move fast enough to approach each other closely, but not quite close enough to overcome their electrical repulsion completely. However, thanks to quantum tunneling, they can pass through the repulsive barrier and fuse together. Without tunneling, the Sun would not shine and we would not exist. Tunneling also occurs in many electronic devices. Scanning tunneling microscopes use the tunneling of electrons between a sharp metal tip and a surface to create images of individual atoms. Flash memory in USB drives relies on electrons tunneling through insulating barriers to store data. Radioactive decay involves particles tunneling out of atomic nuclei. Quantum tunneling is woven throughout the fabric of the physical world. Empty space, we tend to think, is simply nothing. A perfect vacuum contains no matter, no particles, no energy. But quantum mechanics reveals that empty space is far from empty. Due to the uncertainty principle, energy and time cannot both be precisely determined. This means that for very brief moments, energy can fluctuate, allowing particle-antiparticle pairs to spontaneously appear out of the vacuum. These are called virtual particles. An electron and positron pair, or a quark and antiquark pair, can pop into existence, exist for a fleeting instant, and then annihilate back into nothingness before they violate conservation of energy over longer timescales. The shorter the lifetime of these virtual particles, the more energy they can borrow from the vacuum. Space at the quantum level is a seething foam of activity, with virtual particles constantly appearing and disappearing. These virtual particles are not just theoretical abstractions, they have measurable effects. The Casimir effect involves two metal plates placed very close together in a vacuum. Virtual particles with wavelengths larger than the gap between the plates cannot exist in that space, but particles with all wavelengths can exist outside the plates. This creates a tiny imbalance in pressure that pushes the plates together. The effect has been measured precisely, confirming that virtual particles are real. Virtual particles also contribute to the properties of real particles. An electron is surrounded by a cloud of virtual photons and electron-positron pairs that constantly appear and disappear. These virtual particles slightly alter the electron's mass and charge. The self-energy of the electron is infinite in naive calculations, but sophisticated techniques in quantum field theory allow physicists to extract finite, measurable predictions that match experiments with extraordinary precision. Let us turn now to the Pauli exclusion principle, a rule that applies to particles called fermions. Fermions include electrons, protons, neutrons, and quarks. The exclusion principle states that no two identical fermions can occupy the same quantum state at the same time. Two electrons cannot have the same position, momentum, spin, and all other quantum numbers simultaneously. This seemingly abstract rule has profound consequences. It is the reason that matter is solid and takes up space. If electrons in atoms could all occupy the same low-energy state, they would all crowd into the ground state of the atom, and matter would collapse. But the exclusion principle forces electrons to stack up in different energy levels and orbitals. When you try to push your hand through a table, you are really feeling the repulsion between electrons that are being forced into states already occupied by other electrons. The exclusion principle determines the structure of the periodic table of elements. Hydrogen has one electron, which occupies the lowest energy level. Helium has two electrons, filling that lowest level, which can hold two electrons with opposite spins. Lithium has 3 electrons, so the third must go into the next higher energy level. As you add more electrons, they fill increasingly complex orbital patterns, giving each element its unique chemical properties. The principle also explains why white dwarf stars and neutron stars can resist gravitational collapse. When a star runs out of nuclear fuel and collapses, the electrons are squeezed closer and closer together. But the exclusion principle prevents them from occupying the same state, creating a pressure called electron degeneracy pressure that can halt the collapse, forming a white dwarf. In more massive collapsing stars, gravity overcomes electron degeneracy pressure, forcing electrons to combine with protons to form neutrons. Then neutron degeneracy pressure creates a neutron star. Without the Pauli exclusion principle, all matter would collapse into black holes. Particles possess an intrinsic property called quantum spin. Despite the name, this is not actual physical spinning motion. It is a fundamental quantum property that has no true classical analog. However, spin behaves mathematically like angular momentum, and it gives rise to magnetic properties in particles. Electrons have spin 1/2, meaning they can exist in one of two spin states often described as spin up and spin down. These are not references to literal directions in space, but rather to the two possible values of the electron's intrinsic angular momentum. When you measure an electron's spin along any chosen axis, you always get one of two results, never anything in between. The concept of spin emerged from attempts to explain fine details in atomic spectra and the behavior of atoms in magnetic fields. The Stern-Gerlach experiment in 1922 sent silver atoms through a non-uniform magnetic field. Classical physics predicted the atoms would be deflected by varying amounts, creating a continuous smear on a detector screen. Instead, the atoms split into two distinct groups, revealing the quantized nature of spin. Spin has profound consequences. It determines whether a particle is a fermion or a boson. Particles with half-integer spin are fermions and obey the Pauli exclusion principle. Particles with integer spin are bosons and can occupy the same quantum state in unlimited numbers. Photons are spin 1 bosons, which is why you can have many photons in the same state, creating phenomena like lasers. The spin of electrons is responsible for magnetism. Normally, electron spins in a material point in random directions, cancelling out. But in ferromagnetic materials like iron, interactions between electrons cause their spins to align in the same direction over large regions called magnetic domains. This collective alignment of electron spins creates the magnetic fields we observe in permanent magnets. One of the most famous and enlightening experiments in all of physics is the double slit experiment. Originally performed with light in the early 1800s, it has since been repeated with electrons, atoms, and even large molecules, always revealing the same profound truth about quantum mechanics. The setup is simple. You have a barrier with two narrow slits in it and a screen behind to detect what passes through. Fire particles, say electrons, one at a time at the barrier. Classical intuition says each electron should go through one slit or the other and hit the screen somewhere behind that slit. Over time, you would expect to see two bright bands on the screen, one behind each slit. But that is not what happens. Instead, an interference pattern emerges, alternating bands of high and low intensity, just like what you would see if waves were passing through both slits and interfering with each other. Dark bands appear where the wave from one slit arrives out of phase with the wave from the other slit, causing destructive interference. Bright bands appear where the waves arrive in phase, causing constructive interference. The astounding thing is that this happens even when you fire electrons one at a time, with long gaps between them. Each electron somehow interferes with itself, as if it passes through both slits simultaneously as a wave, then manifests as a particle when it hits the screen. The probability distribution of where individual electrons land gradually builds up the interference pattern. But here is where it gets even stranger. If you set up detectors to determine which slit each electron passes through, the interference pattern disappears. The electrons now behave like classical particles, creating two bands on the screen instead of multiple interference bands. The act of measurement changes the outcome. When you measure which slit the electron passes through, you force it to behave like a particle at that moment. When you do not measure, it behaves like a wave passing through both slits. This experiment encapsulates the core mystery of quantum mechanics. The electron exists in a superposition of passing through both slits until a measurement forces it to choose one path. The wave function, which describes the probability of finding the electron at various locations, interferes with itself. But measurement collapses the wave function, transforming quantum probabilities into a definite classical outcome. Finally, we come to the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, who proposed various paradoxes about motion. The quantum Zeno effect states that a quantum system can be prevented from evolving by observing it continuously. If you measure a quantum system's state repeatedly in rapid succession, you can effectively freeze it in its current state. Consider a particle that has some probability per unit time of decaying into other particles. If you observe it once after a long time, there is a significant chance you will find it has decayed. But if you observe it repeatedly at very short intervals, each measurement resets the system, collapsing its wave function back to the initial state. The cumulative probability of finding it decayed becomes very small. Frequent observation suppresses the decay. This seems paradoxical. How can merely looking at something prevent it from changing? The key is that measurement in quantum mechanics is not a passive observation, but an interaction that affects the system. Each measurement projects the system into one of its possible states, typically the state you measured it to be in. If you measure frequently enough, you keep projecting the system back into its initial state before it has time to evolve significantly toward other states. The quantum Zeno effect has been demonstrated experimentally with various quantum systems, including trapped ions and atoms. It has practical implications for quantum computing, where you want to prevent quantum information from degrading due to unwanted interactions with the environment. By carefully applying sequences of measurements or control operations, you can use the quantum Zeno effect to protect fragile quantum states. The universe, at its most fundamental level, operates according to principles that defy our everyday intuition. Particles are also waves. Things exist in multiple states at once until observed. You cannot know everything about a system simultaneously. Particles separated by vast distances remain mysteriously connected. Particles can pass through impenetrable barriers. Empty space teems with virtual particles. Electrons cannot occupy the same state, giving matter its solidity. Particles possess intrinsic spin that generates magnetism. The double-slit experiment shows that observation fundamentally alters reality, and continuous observation can freeze quantum evolution. These principles are not abstract mathematical curiosities, but the foundation of the physical world. They govern the behavior of atoms and molecules, determine the properties of materials, enable the nuclear fusion that powers stars, and open pathways to revolutionary technologies. Quantum mechanics has been tested with extraordinary precision across countless experiments and has never been found wanting. Time itself is not the constant backdrop we imagine it to be. It flows at different rates depending on how fast you move and how deep you are in a gravitational field. This strange truth, predicted by Einstein's theory of relativity, has been confirmed by countless experiments and has practical implications for technologies we use every day. Consider the Global Positioning System, the network of satellites orbiting Earth that tells your phone exactly where you are. These satellites carry extraordinarily precise atomic clocks that broadcast time signals. Your phone receives signals from multiple satellites and uses the tiny differences in arrival times to calculate your position. But there is a complication. Time runs at different rates for the satellites and for you on Earth's surface. The satellites orbit at about 20,000 kilometers altitude, moving at roughly 14,000 kilometers per hour. According to special relativity, moving clocks run slower. At the satellite's speed, this effect causes their clocks to lose about 7 microseconds per day compared to clocks on Earth. But according to general relativity, clocks in weaker gravitational fields run faster. At the satellite's altitude, Earth's gravity is weaker, causing their clocks to gain about 45 microseconds per day. The gravitational effect dominates, so the satellite clocks run fast overall, gaining about 38 microseconds per day. This might seem trivially small, but light travels about 30 centimeters in 1 nanosecond. 38 microseconds translates to about 11 kilometers of error per day. Without correcting for relativistic time dilation, GPS would accumulate errors of tens of meters per day, making it essentially useless within hours. Engineers program the satellite clocks to tick at a slightly different rate before launch, compensating for relativity. Every time you check your location on a map, you are relying on Einstein's equations. Time dilation affects anything that moves or experiences gravity. Astronauts on the International Space Station age slightly slower than people on Earth because they are moving fast, but they also age slightly faster because they are in weaker gravity. The effects nearly cancel, but not exactly. After 6 months in orbit, an astronaut has aged about 0.005 seconds less than if they had stayed on Earth. For objects moving at much higher speeds or in much stronger gravitational fields, the effects become dramatic. When objects move at speeds approaching the speed of light, something equally strange happens to space itself. Length contraction means that objects appear compressed in their direction of motion from the perspective of a stationary observer. A spacecraft traveling at 90% of the speed of light would appear to be less than half its original length to someone watching it pass by. From the perspective of passengers inside the spacecraft, nothing seems unusual. Their spacecraft has its normal length, and they feel no compression. But if they look out at the universe around them, they would see distances shortened in the direction they are traveling. A journey that ground observers measure as 10 light years might appear to the travelers as only about 4 light years due to length contraction. Combined with time dilation, which makes their clocks run slower, they could complete the journey in what feels like much less time than ground observers measure. These are not optical illusions or measurement artifacts. Space and time genuinely behave differently depending on your state of motion. There is no absolute reference frame, no universal clock ticking at the same rate everywhere. Every observer carries their own valid perspective, their own measurements of space and time intervals. What is simultaneous for one observer is not simultaneous for another moving relative to them. Perhaps the most famous equation in all of physics is E equals mc squared. Energy equals mass times the speed of light squared. This deceptively simple formula reveals a profound truth about the universe. Mass and energy are not separate things, but different manifestations of the same underlying quantity. Mass is concentrated energy. Energy has mass. The speed of light, approximately 300 million meters per second, is enormous. When you square it, you get an even more enormous number. This means that a tiny amount of mass corresponds to a colossal amount of energy. 1 kilogram of mass, if converted entirely to energy, would release about 90 petajoules, equivalent to roughly 21 megatons of TNT. This is more energy than the largest nuclear weapons ever detonated. Nuclear weapons derive their devastating power from converting a small fraction of mass into energy. In nuclear fission, heavy atomic nuclei split into lighter fragments. In nuclear fusion, light nuclei combine into heavier ones. In both processes, the total mass of the products is slightly less than the mass of the initial ingredients. The missing mass has been converted to energy, released as light, heat, and kinetic energy of the particles. The sun generates its energy through nuclear fusion, converting about 4 million tons of mass into energy every second. This has been ongoing for nearly 5 billion years, and the sun still has enough mass to continue for another 5 billion years. Stars are mass-to-energy converters operating on a scale that dwarfs anything humanity has ever created. Matter and antimatter can annihilate completely, converting 100% of their mass into energy. When an electron meets a positron, they destroy each other in a flash of gamma rays. This represents the ultimate limit of energy extraction from mass. Antimatter would be the perfect fuel if we could produce and store it efficiently, but currently, it takes far more energy to create antimatter than we can extract from it. Einstein's general theory of relativity revolutionized our understanding of gravity. Newton described gravity as a force of attraction between massive objects, pulling them together across empty space. This picture worked remarkably well for centuries, accurately predicting planetary orbits and the trajectories of projectiles. But Einstein revealed that gravity is not a force at all. It is the curvature of space-time itself. Imagine space-time as a flexible fabric, like a rubber sheet stretched flat. Place a massive object, say a bowling ball, on the sheet. The weight of the ball creates a depression, curving the sheet around it. Now roll a marble across the sheet. It follows a curved path around the depression, not because the bowling ball is pulling on it, but because the sheet itself is curved. The marble is simply following the straightest possible path through the curved space. This is how gravity works in general relativity. Massive objects warp the geometry of space-time around them. Other objects move through this warped space-time, following what are called geodesics, the equivalent of straight lines in curved space. The Earth orbits the Sun, not because the Sun pulls on it, but because the Sun's mass curves space-time, and Earth follows a geodesic through that curved geometry. Light also follows geodesics. When light from a distant star passes close to the Sun's curvature of space-time bends the light's path. During a solar eclipse, stars that should be hidden behind the Sun become visible because their light has been bent around it. This gravitational lensing effect was one of the first confirmations of general relativity observed during the solar eclipse of 1919. The measured deflection of starlight matched Einstein's predictions, catapulting him to worldwide fame. Gravitational lensing is now a powerful tool in astronomy. When light from a distant galaxy passes by a massive cluster of galaxies between us and the distant galaxy, the cluster's gravity bends the light, creating multiple distorted images of the background galaxy. By analyzing these lensed images, astronomers can map the distribution of mass in the foreground cluster, including dark matter that emits no light but reveals its presence through gravitational effects. The curvature of space-time is not static. When massive objects accelerate, particularly when they orbit each other at high speeds, they create ripples in space-time that propagate outward at the speed of light. These are gravitational waves, predicted by Einstein in 1916, but not directly detected until exactly 100 years later. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first confirmed gravitational wave signal. Two black holes, each about 30 times the mass of the Sun, had spiraled together and merged over 1 billion light-years away. In the final fraction of a second before merging, they orbited each other at a significant fraction of the speed of light, releasing tremendous energy as gravitational waves. By the time these waves reached Earth, they had weakened to almost nothing, stretching and compressing space-time by less than 1,000th the diameter of a proton. Yet LIGO's incredibly sensitive instruments detected this minuscule distortion. LIGO consists of two L-shaped detectors, one in Louisiana and one in Washington state. Each arm of the L is 4 kilometers long. Laser beams travel down the arms and reflect back. Normally, the arms have exactly the same length, so the laser beams return in sync. But when a gravitational wave passes through, it stretches one arm while compressing the other, then reverses. The lasers go slightly out of sync, creating an interference pattern that reveals the wave's passing. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, mostly from merging black holes, but also from merging neutron stars. These observations open an entirely new window on the universe. Electromagnetic radiation like light can be absorbed or scattered by matter between the source and us. Gravitational waves pass through matter almost completely unaffected, carrying pristine information about the most violent events in the cosmos, the merger of two. Neutron stars detected in August 2017 was observed as both gravitational waves and electromagnetic radiation, from gamma rays to radio waves. This multi-messenger astronomy allowed scientists to confirm that neutron star mergers are the primary factories for heavy elements like gold and platinum. The gravitational wave signal told us about the masses and dynamics of the merging stars. The electromagnetic signal told us about the physics of the explosion and the material ejected. Space-time responds not just to the presence of mass but also to its motion. A rotating massive object drags space-time around with it, like a spinning ball in honey dragging the honey around it. This phenomenon is called frame dragging, or the Lense-Thirring effect, predicted in 1918. Earth's rotation drags space-time around it, though the effect is extremely small. NASA's Gravity Probe B satellite, launched in 2004, carried gyroscopes of unprecedented precision to measure frame dragging around Earth. The satellite orbited for over a year, measuring tiny changes in the orientation of its gyroscopes. The results, announced in 2011, confirmed frame dragging with an accuracy of about 19%, matching general relativity's predictions. Near rapidly rotating black holes, frame dragging becomes extreme. The region around a rotating black hole is divided into zones. In the ergosphere, just outside the event horizon, space-time is dragged around so strongly that nothing can remain stationary. Everything must rotate in the same direction as the black hole, carried along by the rushing space-time current. It is theoretically possible to extract energy from a rotating black hole through the Penrose process, which exploits frame dragging in the ergosphere. The foundation of Einstein's special theory of relativity is a simple but profound statement. The speed of light in a vacuum is the same for all observers, regardless of their motion relative to the light source. This might seem unremarkable until you think about its implications. Imagine you are standing still and a light beam passes you, traveling at 300 million meters per second. Now imagine you start moving in the same direction as the light beam at half the speed of light. Common sense says you should now measure the light beam traveling at only half its original speed relative to you, just as a car seems slower when you are driving in the same direction. But that is not what happens. You still measure the light beam, traveling at exactly 300 million meters per second. This constancy of the speed of light is not intuitive, but it has been verified by countless experiments. It forced Einstein to abandon the Newtonian concepts of absolute space and absolute time. If light speed is constant for all observers, then space and time themselves must be flexible, adjusting their measurements to keep light speed constant. Time dilation and length contraction follow directly from this principle. The speed of light is not just the speed of light. It is the fundamental speed limit of the universe, the speed at which causality propagates. Anything without mass, including light, gravitational waves, and perhaps other particles, travels at this speed. Anything with mass must travel slower. No matter how much energy you put into accelerating a massive object, you can never quite reach the speed of light. As you approach it, the object's energy increases without limit, and further acceleration becomes impossible. This speed limit has profound implications. It means there are limits to how quickly information can travel across the universe. It creates cosmic horizons, regions of space that are so far away that light from them has not had time to reach us since the universe began. It ensures that cause always precedes effect. Without this speed limit, causality itself might break down. Two events that appear simultaneous to one observer may not be simultaneous to another observer moving relative to the first. This relativity of simultaneity shatters the idea of universal now. There is no cosmic clock that all observers can synchronize to. Different observers slice space-time into space and time differently, depending on their motion. Imagine two lightning bolts strike the ground simultaneously, one at each end of a moving train, as measured by someone standing on the platform. An observer on the platform, positioned exactly midway between the strikes, sees the light from both strikes reach them at the same instant. They conclude the strikes were simultaneous. Now consider an observer on the train, also positioned exactly midway between the two strike locations. The train is moving toward one strike location and away from the other. The light from the strike toward which the train is moving reaches the train observer first. Light from the other strike reaches them later. Since light travels at the same speed for all observers, the train observer concludes that the two strikes were not simultaneous. The strike toward which they were moving happened first. Both observers are correct within their own reference frames. Simultaneity is not absolute, but depends on the observer's state of motion. Events that are simultaneous in one frame are not simultaneous in another frame, moving relative to the first. This seems paradoxical only because our everyday experience involves such low speeds that relativistic effects are imperceptible. At speeds approaching light speed, the effects become obvious and unavoidable. This relativity of simultaneity has strange implications. For events separated by large distances, different observers can disagree not just about when they occurred, but even about the order in which they occurred, as long as the events are not causally connected. However, all observers agree on the causal structure of space-time. If event A causes event B, all observers agree that A happened before B, regardless of their motion. Black holes represent the most extreme manifestation of general relativity. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. If the star is sufficiently massive, nothing can stop the collapse. The core implodes, compressing to infinite density at a point called a singularity, surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. The event horizon is not a physical surface, but a point of no return. Cross it, and space-time is so severely curved that all paths lead inward toward the singularity. There are no outward-pointing trajectories. Light emitted from inside the event horizon curves back inward before it can escape. An observer watching someone fall into a black hole would see them slow down as they approach the event horizon, their image becoming increasingly redshifted and dimmer, frozen at the horizon from the outside observer's perspective. But the infalling observer experiences nothing special at the horizon itself. They simply cross it and continue falling toward the singularity. Near the event horizon, tidal forces can become extreme. Tidal forces arise because gravity is stronger closer to the massive object. For a large black hole, the tidal forces at the event horizon are mild. An astronaut could cross the horizon without being torn apart. But as they fall inward, tidal forces grow rapidly. Eventually, the difference in gravitational pull between their head and feet becomes strong enough to stretch them into a long, thin strand, a process whimsically called spaghettification. Black holes have been indirectly observed through their effects on nearby matter. Gas falling into a black hole forms an accretion disk, heated to millions of degrees by friction, emitting intense X-rays. Stars orbiting close to invisible massive objects reveal the presence of black holes through their motion. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, showing the dark silhouette of the supermassive black hole at the center of the galaxy, Messier 87, surrounded by the glowing accretion disk. Gravitational time dilation affects everything in a gravitational field, even the mundane. Your head is slightly farther from Earth's center than your feet. Earth's gravitational field is slightly weaker at your head than at your feet. Therefore, time passes slightly faster for your head than for your feet. The difference is minuscule, about 10 to the negative 16th of a second per second, but it is real and has been measured. In 2010, physicists at the National Institute of Standards and Technology measured gravitational time dilation over a height difference of just 33 centimeters using atomic clocks accurate to better than 1 part in 10 to the 18th. They confirmed that the higher clock ran faster, precisely matching general relativity's predictions. This experiment brought a cosmic phenomenon into the laboratory, demonstrating that relativity governs not just distant astronomical objects, but also your own body. This means that every part of your body ages at a slightly different rate. Your head ages faster than your feet by an unimaginably tiny amount. Over a human lifetime, the difference amounts to less than a nanosecond. It has no practical effect on biology, but it reminds us that time is not a universal, constant ticking uniformly everywhere. It flows at different rates depending on where you are in space-time. Gravitational time dilation has consequences for precision timekeeping and geodesy. As atomic clocks become more accurate, they become sensitive to smaller gravitational differences. A clock elevated by just 1 centimeter runs measurably faster. This allows clocks to be used as sensitive instruments for measuring Earth's gravitational field and detecting changes in elevation. Future networks of ultra-precise atomic clocks could monitor changes in Earth's gravitational field caused by magma movement, water redistribution, or tectonic plate motion. The universe revealed by relativity is strange and wonderful. Time flows at different rates depending on motion and gravity. Space contracts for moving objects. Mass and energy are equivalent and interconvertible. Gravity is the curvature of space-time. Massive accelerating objects create waves in space-time. Rotating masses drag space-time around them. The speed of light is constant and serves as the ultimate speed limit. Simultaneity depends on the observer. Black holes warp space-time so severely that nothing escapes them. Even your head ages faster than your feet. These are not abstract mathematical curiosities, but fundamental properties of the universe we inhabit. They have been confirmed by countless experiments and observations. They enable technologies we rely on daily. They govern the behavior of stars, galaxies, and the cosmos itself. Relativity transformed our understanding of space, time, matter, and energy, revealing a universe far stranger and more interconnected than anyone imagined. The universe is filled with countless points of light scattered across the night sky. Each one is a star, a massive sphere of plasma held together by its own gravity, powered by nuclear reactions in its core. Stars are the factories of the cosmos, forging the elements that make up planets, life, and everything we see around us. Tonight, we explore the nature of stars, from their fiery births to their dramatic deaths, and the remarkable physics that governs their existence. At the heart of every star burns a nuclear furnace, deep within the core, where temperatures reach millions of degrees and pressures are immense beyond imagination. Hydrogen atoms are forced together to form helium. This process, called nuclear fusion, releases tremendous amounts of energy in the form of light, heat, and radiation. This energy streams outward through the star, eventually escaping from the surface and traveling across space. Some of it reaching our eyes as starlight. The Sun, our nearest star, converts approximately 600 million tons of hydrogen into helium every single second. In this process, about 4 million tons of mass disappear, converted into energy according to Einstein's famous equation: energy equals mass times the speed of light squared. This has been happening continuously for nearly 5 billion years, and the Sun has enough hydrogen remaining to continue for another 5 billion years before it exhausts its fuel. Fusion in stars proceeds through several possible pathways. In stars like the Sun, the proton-proton chain dominates. 4 hydrogen nuclei, which are simply protons, eventually combine through a series of steps to form one helium nucleus, consisting of 2 protons and 2 neutrons. In more massive stars, where core temperatures are higher, a different process called the carbon-nitrogen-oxygen cycle takes over. Carbon acts as a catalyst, temporarily capturing protons and releasing them in a cycle that converts 4 hydrogen nuclei into 1 helium nucleus. The energy released by fusion creates radiation pressure that pushes outward from the core. This outward pressure exactly balances the inward pull of the star's own gravity, creating a stable equilibrium. A star is essentially a continuous balancing act between these two opposing forces. If fusion increases, radiation pressure grows stronger, pushing the outer layers outward. This expansion cools the core slightly, slowing fusion back down. If fusion decreases, gravity compresses the core, heating it and speeding up fusion. This self-regulating mechanism keeps stars stable for billions of years. This balance is called hydrostatic equilibrium. Every layer of a star supports the weight of all the layers above it through its pressure. The deeper you go into a star, the higher the pressure and temperature become, because each layer must support more weight. At the very center, conditions become extreme enough for nuclear fusion to occur. Without fusion to generate pressure, gravity would cause the star to collapse. Without gravity to contain the fusion reactions, the star would explode. The star exists in a delicate dance between these two fundamental forces. The fusion reactions that power the Sun should not be possible according to classical physics. Protons carry positive electric charge, and like charges repel each other. To fuse, 2 protons must approach each other closely enough for the strong nuclear force to bind them together. But the electrical repulsion between protons creates an energy barrier. At the temperatures in the Sun's core, about 15 million degrees, protons collide with considerable energy, but still not enough to overcome the repulsive barrier classically. Quantum mechanics provides the solution. According to quantum tunneling, particles have a small but non-zero probability of passing through energy barriers that they classically cannot surmount. Protons can tunnel through the electrical repulsion barrier and fuse together, even though they lack sufficient classical energy. Without quantum tunneling, the Sun would not shine. The temperature required for classical fusion would be so high that the Sun would burn through its fuel in mere millions of years instead of billions. Quantum tunneling allows fusion to proceed at lower temperatures, extending stellar lifetimes and making the evolution of complex life possible. The probability of tunneling is very small for any individual collision. A proton in the Sun's core might collide with countless other protons over millions of years before successfully tunneling through the barrier and fusing. But the Sun's core contains an enormous number of protons, undergoing an enormous number of collisions every second. Even with tiny individual probabilities, the sheer number of attempts means that fusion occurs at a steady rate, producing the Sun's luminosity. When certain stars die, they leave behind remnants of extraordinary density. A neutron star is one such remnant, formed when a massive star explodes in a supernova and its core collapses. The electrons and protons in the core are forced together, forming neutrons. The result is essentially a giant atomic nucleus about 20 kilometers in diameter, but containing more mass than the Sun. The density of a neutron star defies comprehension. A single cubic centimeter, about the size of a sugar cube, contains roughly 100 million tons of neutron star material. A teaspoonful, about 5 cubic centimeters, would weigh approximately 500 million tons. If you could somehow bring a teaspoon of neutron star material to Earth, it would instantly sink through the ground, punching through bedrock, continuing through the mantle, and falling toward Earth's center. Nothing on Earth could support its weight. Neutron stars are supported against further gravitational collapse by neutron degeneracy pressure, a quantum mechanical effect related to the Pauli exclusion principle. Neutrons, like electrons, are fermions and cannot occupy the same quantum state. When neutrons are compressed to extreme densities, they are forced into higher and higher energy states because lower energy states are already occupied. This creates a pressure that resists further compression. The neutron star represents a balance between gravity trying to compress it further and neutron degeneracy pressure resisting compression. The properties of neutron stars are extreme in every way. Surface gravity is about 100 billion times stronger than on Earth. An object dropped from 1 meter above the surface would hit the ground in a few microseconds, reaching a speed of thousands of kilometers per second. The escape velocity from a neutron star is roughly half the speed of light. Magnetic fields can reach trillions of times the strength of Earth's magnetic field, the strongest magnetic fields known in the universe. When a star like the Sun exhausts the hydrogen in its core, it cannot maintain hydrostatic equilibrium. The core contracts and heats up, while the outer layers expand, transforming the star into a red giant. Helium in the core eventually ignites, fusing into carbon and oxygen. But stars like the Sun cannot generate enough core temperature and pressure to fuse carbon and oxygen into heavier elements. Once helium is exhausted, fusion ceases permanently. White dwarfs are supported against gravitational collapse by electron degeneracy pressure. The electrons in the white dwarf are compressed to extreme densities. The Pauli exclusion principle prevents multiple electrons from occupying the same quantum state, creating a pressure that supports the star even without fusion. This is the same principle that gives ordinary matter its solidity, but in a white dwarf, it operates under far more extreme conditions. A white dwarf can cool indefinitely as a stable object, eventually becoming a black dwarf, a cold, dark cinder of degenerate matter. However, the universe is not old enough for any white dwarfs to have cooled to this state yet. All white dwarfs are still glowing from their residual heat, though many have cooled enough to be quite faint. In the early 1930s, the astrophysicist Subrahmanyan Chandrasekhar calculated that white dwarfs have a maximum possible mass. Electron degeneracy pressure has limits. If a white dwarf exceeds approximately 1.4 times the mass of the Sun, electron degeneracy pressure cannot support it against gravity. The star must collapse further. This critical mass is called the Chandrasekhar limit. A white dwarf near the Chandrasekhar limit that accretes additional mass from a companion star can be pushed over the limit. When this happens, the white dwarf collapses, and the compression reignites carbon fusion explosively throughout the entire star. The star is completely destroyed in a Type Ia supernova, an explosion so bright it can briefly outshine an entire galaxy. Type Ia supernovae are remarkably consistent in their peak brightness because they occur at a well-defined mass limit. This makes them useful as standard candles for measuring cosmic distances. In the late 1990s, observations of distant Type Ia supernovae revealed that the universe's expansion is accelerating, a discovery that led to the concept of dark energy and earned the Nobel Prize in Physics in 2011. If a collapsing stellar core exceeds about 3 solar masses, even neutron degeneracy pressure cannot halt the collapse. Nothing in known physics can prevent the formation of a black hole. The Chandrasekhar limit thus represents a critical threshold in stellar evolution, determining whether a stellar remnant becomes a stable white dwarf, a neutron star, or a black hole. When a massive star runs out of fuel, its core collapses catastrophically in less than a second. The outer layers, no longer supported, fall inward at tremendous speed. The core becomes so dense that the infalling matter rebounds, generating a shock wave that propagates outward through the star. This shock wave blasts the outer layers into space in a core collapse supernova, one of the most energetic events in the universe. A supernova releases approximately 10 to the 46 joules of energy, roughly equivalent to the energy the Sun will radiate over its entire 10 billion year lifetime, but released in just a few weeks. However, most of this energy is not released as light electromagnetic radiation or kinetic energy of the explosion. 99% of the energy is carried away by neutrinos. Neutrinos are fundamental particles that interact extremely weakly with matter. They pass through normal matter as if it barely exists. Trillions of neutrinos from the Sun pass through your body every second without interacting. But in the collapsing core of a supernova, conditions are so extreme that even neutrinos are briefly trapped. When they escape, they carry away most of the supernova's energy. In February 1987, supernova 1987A exploded in the Large Magellanic Cloud, a nearby satellite galaxy. Neutrino detectors on Earth recorded a brief burst of about 24 neutrinos arriving from the direction of the supernova, several hours before the light from the explosion became visible. This confirmed that core collapse supernovae release enormous numbers of neutrinos and provided invaluable data about the explosion. Mechanism: the detection of supernova neutrinos represented a triumph for astrophysics. Out of approximately 10 to the 58 neutrinos released by the supernova, only a couple dozen were detected on Earth due to neutrinos' weak interactions. Yet this tiny sample confirmed theoretical predictions and opened a new window on stellar death. Nuclear fusion in stars proceeds stepwise, building progressively heavier elements. Hydrogen fuses to helium. Helium fuses to carbon and oxygen. In massive stars, carbon fuses to neon and magnesium. Oxygen fuses to silicon and sulfur. Silicon fuses to iron and nickel. Each stage of fusion releases energy because the products are more tightly bound than the reactants. But iron is the end of the line. Iron has the most tightly bound nucleus of any element. Fusing iron into heavier elements requires energy input rather than releasing energy. Stars cannot extract energy by fusing iron. Once a massive star's core becomes iron, fusion ceases and the core collapses, triggering a supernova. Elements heavier than iron are created in the extreme conditions of supernova explosions. As the shockwave propagates through the star, it heats material to billions of degrees. Neutrons are produced in abundance. Atomic nuclei can capture neutrons rapidly, building up heavier and heavier elements before they decay. This rapid neutron capture process, called the R process, creates roughly half of all elements heavier than iron, including gold, platinum, uranium, and thorium. Neutron star mergers also produce heavy elements. When two neutron stars orbit each other, they gradually spiral inward, eventually colliding and merging. The collision ejects neutron-rich material into space, where rapid neutron capture creates heavy elements. The neutron star merger detected in August 2017 by gravitational waves and electromagnetic telescopes produced signatures consistent with the creation of several Earth masses of gold and platinum, every element heavier. Then helium was created inside stars. The oxygen you breathe, the carbon in your cells, the nitrogen in your DNA, the calcium in your bones, the iron in your blood, all were forged in stellar furnaces billions of years ago. When those stars died, they returned this enriched material to space through stellar winds, planetary nebulae, and supernova explosions. This material mixed with interstellar gas clouds, which eventually collapsed to form new generations of stars and planetary systems. Our solar system formed from such a cloud about 4.6 billion years ago, inheriting the heavy elements created by previous generations of stars. The atoms in your body are literally stardust, remnants of stars that lived and died long before the sun existed. This cosmic recycling has been ongoing since the first stars formed. The earliest stars contained only hydrogen and helium, the primordial elements created in the Big Bang. When these stars died, they enriched space with heavier elements. Successive generations of stars incorporated these heavy elements, producing even more. The Sun is a relatively late generation star containing roughly 2% heavy elements by mass. These heavy elements enabled the formation of rocky planets like Earth and, ultimately, life. Some neutron stars spin rapidly, completing hundreds of rotations per second. If such a neutron star possesses a strong magnetic field aligned at an angle to its rotation axis, it acts as a cosmic lighthouse. Charged particles accelerated by the magnetic field emit beams of radiation from the magnetic poles. As the neutron star rotates, these beams sweep through space. If a beam happens to point toward Earth during part of the rotation, we detect a pulse of radiation. These objects are called pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student analyzing data from a radio telescope. She noticed a strange, extremely regular signal repeating every 1.3 seconds. The signal was so precise that it was jokingly nicknamed LGM-1 for Little Green Men before its true nature was understood. Within months, more pulsars were discovered, confirming that they were natural astrophysical objects, not alien transmissions. Pulsars are among the most precise clocks in nature. The best pulsars, called millisecond pulsars, have periods stable to better than 1 part in 10 to the 15th, rivaling atomic clocks. They slow down gradually as they lose rotational energy, but this slowdown is regular and predictable. Arrays of millisecond pulsars are being monitored to detect gravitational waves passing through our region of the galaxy, which would cause tiny correlated timing variations across the array. The extreme density and rapid rotation of pulsars creates unusual physics. The surface of a pulsar moves at a significant fraction of the speed of light. The magnetic field can reach trillions of Gauss, strong enough that quantum effects dominate. Photons can split into electron-positron pairs. Atoms are compressed into needle-like shapes aligned with the field. The crust of a neutron star may contain exotic crystalline structures of nuclei immersed in a sea of electrons, while the interior may contain superfluid neutrons and superconducting protons. Some pulsars show sudden increases in rotation rate called glitches. These occur when the solid crust cracks and settles into a more compact configuration, or when superfluid in the interior suddenly transfers angular momentum to the crust. Studying these glitches provides insights into the properties of matter at densities impossible to recreate in laboratories. Stars dominate the visible universe, but they are finite beings. They are born from collapsing clouds of gas and dust. They live for millions to trillions of years, sustained by nuclear fusion. They die when their fuel is exhausted, leaving behind white dwarfs, neutron stars, or black holes, depending on their mass. Throughout their lives and in their deaths, they enrich the universe with heavy elements, enabling the formation of planets and life. The study of stars reveals the deep connections between quantum mechanics, nuclear physics, general relativity, and astrophysics. Quantum tunneling enables fusion. The Pauli exclusion principle supports stellar remnants. Relativity governs neutron stars and black holes. Nuclear physics determines the pathways of element creation. Stars are laboratories where these fundamental principles play out on cosmic scales. Every star in the night sky is a nuclear furnace, a massive plasma ball held together by gravity and powered by fusion. Every star follows its own evolutionary path determined by its mass. Every star contributes to the chemical enrichment of the galaxy, and every star that has died has left behind elements that became part of new stars, new planets and new possibilities. As you rest tonight, reflect that you are made of atoms forged in the hearts of ancient stars. The hydrogen in your body was created in the Big Bang. The carbon, nitrogen, oxygen, and other essential elements were created in stellar cores and scattered into space by dying stars. You are a temporary arrangement of stardust given consciousness, contemplating the very stars that created you. The iron in your blood once circulated through the core of a massive star, fusing from lighter elements in the final moments before a supernova explosion. The calcium in your bones was blasted into space when that star died. The oxygen you breathe with every breath was expelled from the outer layers of dying red giants. You are intimately connected to the cosmos, a product of billions of years of stellar alchemy. Stars are not eternal, but their legacy endures. The elements they create persist, cycling through generations of stars, accumulating into planets, and eventually into living beings who can look up at the night sky and understand, at least partially, the processes that brought them into existence. You are the universe made conscious, stardust contemplating stars, a temporary focal point of complexity in the vast cosmic dance. In the depths of space, there exist objects so extreme that they warp the very fabric of reality around them. Black holes are regions where gravity has become so intense that nothing, not even light itself, can escape. They are cosmic laboratories where the laws of physics are pushed to their limits, where time and space behave in ways that defy intuition. Tonight, we explore these mysterious objects, from their fundamental properties to the paradoxes they create. Every black hole is surrounded by an invisible boundary called the event horizon. This is not a physical surface that you could touch, but rather a mathematical boundary in space-time. The event horizon marks the point of no return. Any object that crosses this boundary, whether it is a particle, a beam of light, or a spacecraft, can never return to the outside universe. All paths from inside the event horizon lead inexorably inward toward the center. The name event horizon is fitting. It represents a horizon beyond which events cannot be observed from the outside. Light emitted from inside the event horizon curves back inward before it can escape. An observer outside the black hole can never see what happens beyond this boundary. The interior of a black hole is forever hidden from the external universe, sealed off by the extreme curvature of space-time. The size of the event horizon depends on the black hole's mass. For a non-rotating black hole, the radius of the event horizon is called the Schwarzschild radius. It is proportional to the mass. A black hole with the mass of the Sun would have an event horizon radius of about 3 kilometers. A black hole with 10 times the Sun's mass would have a radius of about 30 kilometers. The supermassive black hole at the center of our galaxy, with a mass of roughly 4 million suns, has an event horizon radius of about 12 million kilometers, roughly 17 times the radius of the Sun. Nothing special happens at the event horizon itself for someone falling through it. You would not notice anything unusual as you crossed. There is no wall, no barrier, no sudden change. You would simply continue falling, unaware that you had just passed the point of no return. Only later, when you tried to send a signal outward or turn around, would you discover that escape is impossible. Every direction you could travel now leads deeper inward, toward the singularity at the center. The gravitational field around a black hole is not uniform. Gravity is stronger closer to the black hole and weaker farther away. This difference in gravitational strength across an extended object creates tidal forces. If you were falling feet first toward a black hole, your feet would experience stronger gravity than your head. This difference in force would stretch you vertically. Simultaneously, gravitational forces would compress you horizontally, squeezing you from the sides. For stellar mass black holes, those form from collapsed stars with masses of a few to a few dozen times the Sun's mass. These tidal forces become extreme well before you reach the event horizon. The difference in gravity between your head and your feet would grow so large that you would be stretched longer and thinner, like a piece of taffy being pulled. Eventually, the forces would overcome the molecular bonds holding your body together. You would be torn apart into a thin stream of atoms, a process scientists have whimsically named spaghettification. Interestingly, for supermassive black holes millions or billions of times more massive than the Sun, the event horizon is much larger, and the tidal forces at the horizon are much weaker. You could cross the event horizon of a supermassive black hole without being immediately torn apart. You would fall through still intact, completely unaware that you had crossed into a region from which there is no escape. Only as you fell closer to the singularity at the center would tidal forces grow strong enough to destroy you. The tidal forces grow without limit as you approach the center of the black hole. No matter how strong a material might be, no matter what forces hold atoms together, the tidal forces eventually become so extreme that everything is shredded into elementary particles and then compressed to infinite density at the singularity. This singularity is a point where space-time curvature becomes infinite, where the equations of general relativity break down, and where our understanding of physics fails. In classical general relativity, black holes are remarkably simple objects. Despite forming from the collapse of complex stars with intricate distributions of matter, rotation, magnetic fields, and other properties, the final black hole retains only three characteristics: its mass, its electric charge, and its angular momentum or spin. Everything else is erased. This principle is known as the no-hair theorem, suggesting that black holes have no distinguishing features beyond these three properties. Two black holes with the same mass, charge, and spin are completely identical, regardless of what fell into them to create them. One might have formed from the collapse of a star made of normal matter. Another might have formed from a star made entirely of antimatter. A third might have formed from pure energy, compressed to sufficient density. Once they settle down after formation, if they have the same mass, charge, and spin, they are indistinguishable. All the information about what went into making them has been lost. In practice, black holes in the universe are expected to be electrically neutral or nearly so. Any significant electric charge would attract opposite charges from the surrounding environment, quickly neutralizing the black hole. So the two properties that really matter for astrophysical black holes are mass and spin. Mass determines the size of the event horizon and the strength of the gravitational field. Spin determines how the black hole drags space-time around it. Non-rotating black holes are described by the Schwarzschild solution to Einstein's equations, discovered in 1916. Rotating black holes are described by the Kerr solution, found in 1963. The Kerr solution is more complex, featuring not just an event horizon, but also an outer boundary called the ergosphere, where space-time is dragged around the black hole so strongly that nothing can remain stationary. Everything in the ergosphere must rotate in the same direction as the black hole, carried along by the flow of space-time itself. At the center of nearly every large galaxy lies a supermassive black hole. These giants have masses millions to billions of times greater than the Sun. Our own Milky Way galaxy harbors a supermassive black hole called Sagittarius A star, with a mass of approximately 4 million suns, located about 26,000 light-years from Earth at the galactic center. For decades, astronomers tracked stars orbiting near the galactic center with extraordinary precision. These stars move at speeds reaching thousands of kilometers per second, completing orbits in as little as 15 years. By measuring their orbits, astronomers determined that they are orbiting an invisible, massive object confined to a very small region. The only object that can be so massive and so compact is a black hole. In 2020, Andrea Ghez and Reinhard Genzel shared the Nobel Prize in Physics for this work. providing the most compelling evidence for supermassive black holes. The black hole at the center of our galaxy is relatively quiet. It accretes very little material and emits relatively weak radiation. But some supermassive black holes are surrounded by enormous accretion disks of gas and dust spiraling inward. Friction in the accretion disk heats the material to millions of degrees, causing it to emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays. These actively accreting supermassive black holes power some of the brightest objects in the universe, called quasars, or active galactic nuclei. The brightest quasars can outshine their entire host galaxies, radiating more energy than hundreds of billions of stars combined, all from a region smaller than our solar system. This tremendous luminosity is powered by matter falling into the supermassive black hole. As matter spirals inward, it converts gravitational potential energy into heat and radiation. Supermassive black holes are the most efficient engines in the universe for converting mass into energy, far more efficient than nuclear fusion in stars. The origin of supermassive black holes remains somewhat mysterious. They exist in the early universe, less than 1 billion years after the Big Bang, which seems like insufficient time for them to grow to billions of solar masses by accreting matter. They may have formed from the collapse of massive primordial gas clouds, or from the merger of many smaller black holes, or through other mechanisms not yet fully understood. Unraveling their origin is an active area of research in astrophysics. In 1974, Stephen Hawking made a remarkable discovery by applying quantum field theory to the curved spacetime near a black hole's event horizon. He found that black holes are not entirely black. They emit a faint thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. Quantum field theory tells us that empty space is filled with fluctuations, virtual particle-antiparticle pairs constantly popping into and out of existence. Near a black hole's event horizon, something unusual can happen. A virtual pair can be created with one particle just inside the horizon and one just outside. The particle inside falls into the black hole while the particle outside escapes to infinity. To an outside observer, it appears as if the black hole has emitted a particle. This process is not free. The escaping particle carries away energy. For energy to be conserved, the black hole must lose mass. Over time, the black hole slowly evaporates as it radiates Hawking radiation. The temperature of this radiation is inversely proportional to the black hole's mass. Stellar mass. Black. Holes have incredibly low temperatures, far below the cosmic microwave background, so they absorb more energy than they radiate and actually grow. But in the distant future, when the universe has cooled, or for very small black holes, Hawking radiation dominates. For a black hole with the mass of the Sun, the temperature is about 1/10,000,000th of a degree above absolute zero. The time required for such a black hole to evaporate completely is approximately 10 to the 67 years, an unimaginably long time, vastly exceeding the current age of the universe. More massive black holes have even lower temperatures and even longer evaporation times. The supermassive black holes at galactic centers will take 10 to the 100 years or more to evaporate. But if small black holes exist, with masses much less than the Sun, they could have higher temperatures and shorter evaporation times. A black hole with a mass of about 100 million tons would have a temperature around room temperature and would evaporate in a few billion years. An even smaller black hole with a mass of a large asteroid would be hot enough to glow and would evaporate in seconds, exploding in a burst of gamma rays. Hawking radiation has never been directly observed because the effect is so weak for astrophysical black holes. However, Analogous effects have been observed in laboratory systems that mimic black hole horizons, such as flowing fluids and acoustic systems. These analog systems support Hawking's theoretical predictions and have opened new avenues for studying quantum effects in curved space-time. Time behaves strangely near a black hole due to gravitational time dilation. Clocks in stronger gravitational fields run slower than clocks in weaker fields. Near a black hole, this effect becomes extreme. An observer far from the black hole, watching something fall toward the event horizon, would see the falling object slow down as it approaches. Light from the falling object would become increasingly redshifted, making the object dimmer and redder. From the distant observer's perspective, the falling object never quite reaches the event horizon. It appears to freeze at the horizon, its image becoming ever dimmer and more redshifted, fading away asymptotically. Time appears to stop at the event horizon. The object's clock, as seen by the distant observer, ticks slower and slower, approaching zero rate at the horizon. But this is only from the perspective of the distant observer. For the falling object itself, nothing unusual happens at the event horizon. Their clock continues ticking normally. They cross the horizon in a finite amount of their own time, called proper time. They do not notice time slowing down or stopping. They simply fall through and continue inward. This difference in perspectives is one of the strange consequences of relativity. Different observers measure time differently. There is no universal clock that all observers agree on. The distant observer and the falling observer have fundamentally different experiences of the same event. For the distant observer, the fall takes infinite time. For the falling observer, it takes only seconds or minutes. Once inside the event horizon, the roles of time and space are, in a sense, reversed. Outside the horizon, you can move freely in space, but are carried inexorably forward in time. Inside the horizon, you can move freely through what was time, but you are carried inexorably inward in space toward the singularity. The singularity is not a place in space, but rather an event in your future, unavoidable once you cross the horizon. Black holes need not be stationary. They can rotate, possessing angular momentum from the matter that formed them or fell into them. A rotating black hole is described by the Kerr metric, which features more complex geometry than a non-rotating black hole. The rotation drags space-time around the black hole, creating a region called the ergosphere outside the event horizon. In the ergosphere, space-time is dragged around the black hole so strongly that nothing can remain stationary. Even if you fired your rockets at full power, you could not hover in place. You would be swept around the black hole, carried by the rotating space-time current. However, you could still escape from the ergosphere. It lies outside the event horizon. You are not trapped. You just cannot remain still. The event horizon of a rotating black hole is smaller than that of a non-rotating black hole of the same mass. The faster the black hole spins, the smaller the event horizon becomes. There is a maximum possible rotation rate at which the event horizon would shrink to zero, exposing the singularity. However, this maximally rotating state, called an extremal black hole, is likely impossible to achieve in nature. Any real black hole probably rotates at less than the maximum rate. The rotation of a black hole has observable effects. The accretion disk around a rotating black hole is affected by frame dragging, causing the inner regions to precess and emit radiation in characteristic patterns. Jets of particles and radiation often emerge from the poles of rotating black holes, powered by the extraction of rotational energy through complex electromagnetic processes. Observations of these phenomena allow astronomers to estimate the spin rates of black holes. In principle, it is possible to extract energy from a rotating black hole through a process called the Penrose process. An object entering the ergosphere could split into two parts. with one part falling into the black hole, and the other escaping with more energy than the original object. The extra energy comes from the black hole's rotational energy, causing the black hole to spin more slowly. This is a theoretical mechanism for tapping the enormous energy reservoir of a rotating black hole. Quantum mechanics is built on the principle that information is never lost. If you know the quantum state of a system at one time, you can, in principle, calculate its state at any other time. The evolution of quantum systems is unitary and reversible. Information is conserved. However, black holes seem to violate this principle, leading to the black hole information paradox. When matter falls into a black hole, information about its quantum state seems to disappear. According to classical general relativity, the matter crosses the event horizon and is destroyed at the singularity. The outside universe retains no record of what fell in, beyond the contribution to the black hole's mass, charge, and spin. If the black hole later evaporates via Hawking radiation, which is thermal and contains no information about what fell in, then the original information appears to be lost forever. This conflicts with quantum mechanics. Information cannot simply vanish. The paradox has puzzled physicists for decades. Stephen Hawking initially believed that information is genuinely lost in black holes, that quantum mechanics needs to be modified. But most physicists found this unacceptable. Information loss would undermine the foundations of quantum theory and create inconsistencies in physics. In 2004, Hawking conceded that information is probably not lost, though the mechanism for its preservation remains unclear. One possibility is that information is encoded in subtle correlations in the Hawking radiation, in ways too complex to calculate with current tools. Another possibility is that information is stored at the event horizon, perhaps in a holographic manner. A third possibility is that black holes leave behind remnants containing the information when they evaporate. The true resolution of the paradox remains one of the deepest open questions in theoretical physics, touching on the nature of space-time, quantum gravity, and the fundamental laws of the universe. Most black holes form from the collapse of massive stars at the ends of their lives. But in the early universe, conditions were very different. In the first fraction of a second after the Big Bang, the universe was extremely hot and dense. Random fluctuations in density could have caused some regions to become dense enough to collapse directly into black holes without needing a star. These are called primordial black holes. Primordial black holes could have a wide range of masses, from much less than the mass of the Sun to thousands of solar masses. Very small primordial black holes, if they exist, would have evaporated by now due to Hawking radiation. But black holes with masses above a certain threshold would still exist today, scattered throughout the universe. Primordial black holes have been proposed as a possible explanation for dark matter, the mysterious invisible substance that makes up most of the matter in the universe. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. It reveals its presence only through gravitational effects. Primordial black holes would also be invisible and would interact only gravitationally, fitting the profile of dark matter, however. Searches for primordial black holes have placed strong constraints on how many could exist. Observations of gravitational lensing, where black holes passing in front of distant stars briefly magnify their light, have ruled out primordial black holes as the dominant form of dark matter for most mass ranges. Some mass windows remain open, but most physicists believe dark matter consists of yet undiscovered elementary particles rather than black holes. The detection of gravitational waves from merging black holes by LIGO and Virgo has raised new interest in primordial black holes. Some of the black holes detected have masses that are difficult to explain through standard stellar evolution. They might be primordial black holes formed in the early universe. Further observations will help determine whether primordial black holes exist and, if so, how abundant they are. Although crossing the event horizon is fatal in the long term, due to the inevitable encounter with the singularity, it is theoretically possible to orbit a black hole stably just outside the event horizon. The mathematics of general relativity allows for stable circular orbits at various distances from the black hole, including orbits very close to the horizon. The innermost stable circular orbit depends on the black hole's spin. For a non-rotating black hole, the innermost stable orbit is at 3 times the Schwarzschild radius, or 1.5 times the diameter of the event horizon. For a maximally rotating black hole, stable orbits can exist much closer, almost touching the event horizon. Inside the innermost stable orbit, any small perturbation causes objects to spiral inward and fall into the black hole. An object in a stable orbit just outside the event horizon would experience extreme gravitational time dilation. Its clock would run much slower than clocks far from the black hole. It would orbit at a significant fraction of the speed of light, completing an orbit in a fraction of a second as measured by its own clock. An observer far away would see the object orbiting more slowly due to time dilation, but still incredibly fast. In principle, a spacecraft with sufficiently advanced propulsion could orbit near a black hole indefinitely. The crew would experience time passing slowly relative to the outside universe. They could orbit for what feels like hours, then return to find that centuries have passed elsewhere. This is a form of time travel into the future, permitted by general relativity, though the enormous gravitational forces and engineering challenges make it impractical with any conceivable technology. Black holes represent the ultimate extremes of gravity and space-time curvature. They challenge our understanding of physics at the deepest levels. They are cosmic laboratories where quantum mechanics and general relativity collide, creating paradoxes that point toward a deeper theory of quantum gravity that we do not yet possess. The event horizon marks the boundary beyond which escape is impossible. Tidal forces near black holes stretch and compress matter. Black holes are characterized by just 3 properties, despite the complexity of their formation. Supermassive black holes lurk at the centers of galaxies. Hawking radiation predicts their slow evaporation. Time appears to stop at the event horizon for distant observers. Rotating black holes drag space-time around them. The information paradox questions what happens to information that falls in. Primordial black holes might have formed in the early universe, and stable orbits just outside the horizon are theoretically possible. The universe has not always existed. It had a beginning, a moment of creation when time itself came into being. Approximately 13.8 billion years ago, everything that exists today, all matter, all energy, all of space and time itself, emerged from an incredibly hot, dense state in an event we call the Big Bang. This is not merely a theory, but a conclusion drawn from multiple lines of compelling evidence that converge on this remarkable fact. The age of the universe has been determined through several independent methods, all yielding consistent results. Astronomers measure the expansion rate of the universe and trace it backward in time to find when everything was compressed into a single point. They measure the ages of the oldest stars, which cannot be older than the universe itself. They analyze the cosmic microwave background radiation, the afterglow of the Big Bang, which encodes information about the early universe. All these methods point to an age of approximately 13.8 billion years, with an uncertainty of only about 20 million years. This finite age has profound implications. It means there was a time before which nothing existed in any form we understand. No matter, no energy, no space, not even time itself. The concept of before the Big Bang may be meaningless, like asking what is north of the North Pole. Time began with the Big Bang. The universe did not explode into pre-existing space. Space itself came into existence and has been expanding ever since. The universe is not static. It is dynamic, evolving, expanding. Every galaxy beyond our local cluster is moving away from us, and the more distant the galaxy, the faster it recedes. This observation, first made by Edwin Hubble in the 1920s, revolutionized our understanding of the cosmos and provided the first evidence for the Big Bang. Imagine the universe as the surface of a balloon being inflated. Galaxies are like dots drawn on the balloon's surface. As the balloon expands, every dot moves away from every other dot. From the perspective of any single dot, all other dots appear to be moving away. The farther away another dot is, the faster it seems to recede, because there is more stretching rubber between them. This is analogous to how space itself expands, carrying galaxies along with it. The expansion of the universe means that space itself is stretching. Galaxies are not moving through space in the conventional sense. Rather, the space between them is growing. Light traveling through this expanding space gets stretched as well, increasing its wavelength. This stretches visible light toward the red end of the spectrum, an effect called cosmological redshift. By measuring the redshift of distant galaxies, astronomers can determine how much the universe has expanded since the light was emitted, and thus how far away and how long ago the light originated. The expansion rate is quantified by the Hubble constant, which relates a galaxy's distance to its recession velocity. Current measurements place the Hubble constant at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.3 million light years, a galaxy recedes an additional 70 kilometers per second faster. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second, and so on. At sufficiently large distances, galaxies recede faster than the speed of light. This does not violate relativity, because the galaxies are not moving through space faster than light. Space itself is expanding, and there is no limit to how fast space can expand. Light from these extremely distant galaxies may never reach us, because the space between us and them is expanding faster than light can traverse it. These galaxies lie beyond our cosmic horizon, forever unreachable and unobservable. In every direction we look, space is filled with faint microwave radiation with a temperature of approximately 2.7 degrees above absolute zero. This is the cosmic microwave background, or CMB, the oldest light in the universe, a relic from when the cosmos was only 380,000 years old. It is the most important observation in cosmology, providing a snapshot of the universe in its infancy and confirming the Big Bang theory beyond reasonable doubt. In the first few 100,000 years after the Big Bang, the universe was too hot for atoms to form. Electrons and nuclei existed as a plasma, opaque to light because photons constantly scattered off free electrons. As the universe expanded and cooled, it eventually became cool enough for electrons and nuclei to combine into neutral atoms, mostly hydrogen and helium. This process, called recombination, made the universe transparent to light. The photons that had been trapped in the plasma were suddenly free to travel through space. Those photons are what we see today as the cosmic microwave background. When the CMB was emitted, it was visible light from a glowing plasma at about 3,000 degrees. But 13.8 billion years of cosmic expansion has stretched those photons, increasing their wavelength by a factor of about 1,000. Visible light has been stretched into microwave radiation. The universe has cooled from 3,000 degrees to less than 3 degrees above absolute zero. The CMB fills all of space uniformly, coming from every direction with nearly the same intensity and temperature. Nearly, but not exactly. Careful measurements reveal tiny temperature variations, about 1 part in 100,000. Some regions are slightly warmer, others slightly cooler. These tiny fluctuations are the seeds of all structure in the universe today. Regions that were slightly denser in the early universe had slightly more gravity, attracting more matter over time. Over billions of years, these small overdensities grew into galaxies, galaxy clusters, and the vast cosmic web of structure we see today. The pattern of temperature fluctuations in the CMB encodes information about the composition, geometry, and history of the universe, allowing cosmologists to measure fundamental parameters with extraordinary precision. The Big Bang theory predicts that the universe should be much more irregular than it appears. Different regions of the early universe should have had different temperatures, densities, and properties because they were too far apart to have influenced each other. Light had not had time to travel between them. Yet the CMB shows that the universe is remarkably uniform. Temperature variations are only 1 part in 100,000. How did regions that could not have communicated end up so similar? The answer is cosmic inflation, a period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang. In an almost unimaginably brief interval, perhaps 10 to the negative 35 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26, possibly much more. A region smaller than a subatomic particle inflated to larger than the observable universe today, all in less time than it takes light to cross an atomic nucleus. Before inflation, the region that would become our observable universe was small enough that all parts of it were in contact, able to reach thermal equilibrium. Inflation then stretched this tiny, smooth region to enormous size, preserving its uniformity. This explains why the universe looks the same in all directions. It also explains why the universe is geometrically flat. Any initial curvature was stretched out by the exponential expansion, just as the surface of a balloon appears flatter as it inflates. Inflation also explains the origin of structure. Quantum fluctuations in the inflating universe, tiny random variations at the subatomic scale, were stretched to cosmic size by inflation. These quantum fluctuations became the density variations we see in the CMB, which grew over billions of years into galaxies and galaxy clusters. Everything we see today, all structure in the universe, originated from quantum fluctuations in the first fraction of a second after the Big Bang, amplified to astronomical scales by cosmic inflation. The evidence for inflation is compelling but indirect. It explains multiple otherwise puzzling observations: the uniformity of the CMB, the flatness of space, the spectrum of density fluctuations. However, we do not yet understand what caused inflation. What field or mechanism drove the exponential expansion, or exactly when and how inflation ended? These questions remain at the frontier of cosmological research. In the late 1990s, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe is not slowing down, as had been expected due to the gravitational pull of matter. Instead, the expansion is accelerating. Distant galaxies are moving away from us faster and faster over time. This discovery, which earned the Nobel Prize in Physics in 2011, revealed the existence of a mysterious component called dark energy. Dark energy is a form of energy that permeates all of space uniformly, not clumping into galaxies or clusters. Its defining characteristic is that it exerts negative pressure, causing space to expand. Unlike matter, whose gravity attracts and pulls things together, dark energy pushes space apart. The more space there is, the more dark energy there is, and the stronger its repulsive effect becomes. As the universe expands, matter becomes more dilute, but dark energy remains constant in density. Eventually, dark energy dominates, driving the acceleration we observe. According to current measurements, dark energy constitutes approximately 68% of the total energy content of the universe. Yet we have almost no understanding of what it is. The simplest explanation is that dark energy is the vacuum energy of empty space itself, a constant energy density associated with the quantum properties of the vacuum. This is related to the cosmological constant that Einstein introduced into his equations and later called his greatest blunder. However, naive calculations of vacuum energy yield values that are vastly, absurdly larger than the observed dark energy density. Reconciling these predictions is one of the greatest unsolved problems in theoretical physics. Alternative explanations propose that dark energy is a dynamic field that changes over time, called quintessence, or that our understanding of gravity needs to be modified on cosmic scales. Extensive observational programs are underway to measure the properties of dark energy more precisely, searching for clues about its nature. Understanding dark energy is essential for predicting the ultimate fate of the universe. Most of the matter in the universe is invisible. Galaxies contain far more mass than can be accounted for by stars, gas, and dust. This hidden matter reveals its presence through gravitational effects. Stars at the edges of galaxies orbit faster than can be explained by the visible matter. Galaxies in clusters move faster than the visible matter in the cluster can gravitationally bind. Light from distant galaxies is bent by the gravity of invisible matter in intervening galaxy clusters. All these observations point to the existence of dark matter. Dark matter does not emit, absorb, or reflect light. It does not interact electromagnetically at all. It interacts only through gravity and possibly through the weak nuclear force. It passes through ordinary matter almost without interacting, like a ghost passing through walls. Yet dark matter is not rare. It makes up approximately 27% of the universe, far outweighing ordinary matter, which constitutes only about 5%. Dark matter forms the gravitational scaffolding on which galaxies are built. In the early universe, dark matter began clumping together under its own gravity. These clumps created gravitational wells into which ordinary matter fell, forming the first galaxies. Computer simulations of structure formation show that without dark matter, galaxies and galaxy clusters would not form the way we observe. The distribution of dark matter determines the large-scale structure of the universe, the cosmic web of filaments and voids that spans billions of light years. Despite its abundance and importance, we do not know what dark matter is made of. It is not ordinary matter, not atoms or molecules. The leading candidate is a new type of elementary particle that has not yet been discovered, perhaps a weakly interacting massive particle, or WIMP. Extensive experiments have searched for dark matter particles, both by trying to detect them directly as they pass through detectors on Earth, and by searching for signals of dark matter annihilation or decay in space. So far, these searches have not found conclusive evidence. The nature of dark matter remains one of the deepest mysteries in physics. The universe is vast almost beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Yet we can see only a finite portion of it. The observable universe is limited by the finite age of the universe and the finite speed of light. Light from regions farther than a certain distance has not had time to reach us since the Big Bang. This defines the edge of the observable universe, our cosmic horizon. One might think that the radius of the observable universe should be 13.8 billion light-years. The distance light travels in the age of the universe, but the universe has been expanding while the light was traveling. The galaxies that emitted the cosmic microwave background were only about 42 million light-years away when they emitted the light we see today. But during the 13.8 billion years that light has been traveling toward us, space has expanded, carrying those galaxies much farther away. Today, those galaxies are about 46 billion light-years away. This is the radius of the observable universe. The full diameter is about 93 billion light-years. Beyond the observable universe, space continues. There is no edge, no wall. If you could somehow travel faster than light or wait an infinite time, you could reach those distant regions. But they are forever beyond our observations because their light has not had time to reach us. As the universe ages, our observable region grows. Galaxies that are currently beyond our horizon will eventually become visible as their light reaches us. However, because the expansion is accelerating due to dark energy, some galaxies that are currently observable will eventually recede beyond our horizon, disappearing from view forever. The observable universe contains an estimated 2 trillion galaxies. Each galaxy contains billions to trillions of stars. The total number of stars in the observable universe is perhaps 10 to the 24, a number so large as to be almost meaningless. Yet all of this is only the portion of the universe we can see. The entire universe may be vastly, perhaps infinitely, larger than the observable part. The geometry of space itself can be measured. Space might be positively curved like the surface of a sphere, where parallel lines eventually meet and triangles have angles summing to more than 180 degrees. Space might be negatively curved like a saddle, where parallel lines diverge and triangles have angles summing to less than 180 degrees. Or space might be flat, with Euclidean geometry, where parallel lines remain parallel, and triangles have angles summing to exactly 180 degrees. Observations of the cosmic microwave, background, and the large-scale distribution of galaxies have measured the curvature of space with high precision. The results indicate that the universe is flat, or very close to flat, to within measurement uncertainties of less than 1%. On the larger scales, space has Euclidean geometry. This flatness is not a coincidence, but a consequence of cosmic inflation, which stretched any initial curvature to imperceptible levels. Flatness has implications for the ultimate size of the universe. A positively curved universe is finite, like the surface of a sphere. A flat or negatively curved universe can be infinite. If the universe is truly flat and extends infinitely, then it contains infinite matter and infinite stars. Every possible arrangement of atoms, every possible history, may exist somewhere in an infinite universe, repeated infinitely many times. The philosophical and scientific implications are profound, though untestable. In the early universe, matter and antimatter should have been created in equal amounts. The laws of physics treat matter and antimatter almost symmetrically. When matter and antimatter meet, they annihilate, converting to energy. If equal amounts existed, they should have annihilated completely, leaving a universe filled only with radiation, no matter at all. Yet we live in a universe made of matter. Galaxies, stars, planets, and we ourselves are made of matter, not antimatter. Why? There must have been a small asymmetry in the early universe, a slight excess of matter over antimatter, about one extra matter particle for every billion matter-antimatter pairs. When matter and antimatter annihilated, this tiny excess remained, becoming all the matter we see today. The radiation from the annihilation became the cosmic microwave background, but the question remains, why was there this asymmetry? The conditions necessary for creating a matter-antimatter asymmetry are understood, at least in principle. They were outlined by the physicist Andrei Sakharov. The universe must violate certain symmetries, must be far from thermal equilibrium, and must proceed through interactions that violate the conservation of baryon number. The standard model of particle physics contains mechanisms that satisfy these conditions, but the predicted asymmetry is far too small to explain observations. This suggests that new physics beyond the standard model is required. Perhaps there are additional particles or interactions that generate the observed asymmetry. Perhaps the asymmetry is related to the matter-antimatter differences already observed in certain particle decays, which violate a symmetry called CP symmetry. Perhaps it is connected to the physics of neutrinos or to processes that occurred during inflation. The origin of the baryon asymmetry, why we live in a matter-dominated universe, remains an open question at the intersection of cosmology and particle physics. The universe is evolving toward an ultimate fate determined by its composition and the laws of physics. Given that dark energy dominates and the expansion is accelerating, the most likely long-term future is a cold, dark, nearly empty cosmos. This scenario is sometimes called the heat death of the universe. As the universe expands and accelerates, galaxies beyond our local group will recede beyond the cosmic horizon, disappearing from view. Eventually, only our local group of gravitationally bound galaxies will remain visible. Stars will continue forming for trillions of years, but as gas is exhausted, star formation will cease. Existing stars will die, becoming white dwarfs, neutron stars, or black holes. The universe will grow darker. After 10 to the 40 years or so, even protons may decay, if theoretical predictions are correct, dissolving the remaining matter into radiation. Black holes will slowly evaporate via Hawking radiation over timescales of 10 to the 100 years. Eventually, the universe will contain only dilute radiation and perhaps some exotic particles spread ever thinner by ongoing expansion. The temperature will approach absolute zero. No gradients will exist, no structure, no complexity. The universe will reach a state of maximum entropy, thermal equilibrium, where no energy flows and no processes occur. Time, in a practical sense, will have stopped. This fate is called heat death, though it is really a cold death, a universe frozen in stasis at near absolute zero. It is the ultimate consequence of the second law of thermodynamics, that entropy always increases. The universe is running down like a clock, and eventually the clock will stop. However, this endpoint lies so far in the future, vastly beyond the current age of the universe, that it remains almost purely theoretical. Alternative fates are possible if dark energy behaves differently than currently observed. If dark energy strengthens over time, it could lead to a big rip, where accelerating expansion eventually tears apart galaxies, stars, planets, and even atoms. If dark energy weakens or reverses, the universe could eventually stop expanding and recollapse in a big crunch, returning to a hot, dense state. Current observations favor continued accelerating expansion and heat death, but future measurements may reveal surprises. The universe began 13.8 billion years ago in the Big Bang. It has been expanding ever since, carrying galaxies apart. The cosmic microwave background provides a baby picture of the universe, showing how it looked just 380,000 years after its birth. Cosmic inflation in the first fraction of a second set the initial conditions for structure formation. Dark energy drives the accelerating expansion, making up most of the universe's energy content. Dark matter provides the gravitational scaffolding for galaxy formation, far outweighing ordinary matter. The observable universe is finite, limited by light travel time. The large-scale geometry of space is flat. A slight matter-antimatter asymmetry allowed matter to survive annihilation. The ultimate fate is likely a cold, dark, maximally entropic state. These are the broad strokes of cosmic history from beginning to end. The universe has a story, a narrative arc from birth through evolution to an eventual endpoint. We find ourselves at a remarkable moment in this story, when stars still shine, galaxies still form, and complexity flourishes. The universe is young, barely out of its infancy, with the vast majority of its history still ahead. The universe is stranger and grander than our ancestors imagined. It had a beginning. It is dynamic and evolving. Most of it is invisible, dark matter and dark energy whose nature we barely understand. It may be infinite in extent, containing infinite matter and infinite possibilities. And it is temporary, destined to fade into cold darkness over timescales that dwarf all human experience. The universe operates according to rules, fundamental laws that govern every interaction, every motion, every transformation. At the deepest level, all the complexity we observe, from the falling of raindrops to the fusion of stars, from the firing of neurons to the collision of galaxies, arises from just 4 fundamental forces. These forces shape reality itself, determining how particles interact, how matter behaves, and how the cosmos evolves. Tonight, we explore these fundamental forces and the elegant framework physicists have constructed to understand them. Everything that happens in the universe involves one or more of 4 fundamental forces. Gravity holds planets in orbit around stars and binds galaxies together. Electromagnetism governs the interactions of charged particles, creating light, electricity, magnetism, and the chemical bonds that form molecules. The strong nuclear force binds quarks into protons and neutrons and holds atomic nuclei together, despite the electrical repulsion between protons. The weak nuclear force governs radioactive decay and plays a crucial role in the nuclear reactions that power the sun. These 4 forces have very different characteristics. They operate over different ranges, have different strengths, and affect different types of particles. Gravity and electromagnetism are long-range forces, extending across infinite distances, though weakening with distance. The strong and weak nuclear forces are short-range, operating only over distances comparable to the size of an atomic nucleus or smaller. The forces also differ tremendously in strength. When compared at similar scales, the strong force is the most powerful, followed by electromagnetism, then the weak force, with gravity being by far the weakest. Every force in nature reduces to one of these four. When you push a book across a table, you might think you are exerting a new kind of force, but you are actually exerting electromagnetic force. The electrons in the atoms of your hand repel the electrons in the atoms of the book, creating the sensation of solidity and allowing you to push. Friction between the book and table is also electromagnetic, arising from interactions between atoms at the surfaces. When a star shines, gravity compresses the core, while the strong and weak forces enable nuclear fusion, and electromagnetic radiation carries the energy away as light. Every phenomenon traces back to these four fundamental interactions. The strong nuclear force is the most powerful force in nature. It binds quarks together to form protons, neutrons, and other particles called hadrons. 3 quarks bound by the strong force form a proton or neutron. The binding is so tight that quarks have never been observed in isolation. You cannot pull a quark out of a proton. If you try to separate quarks by applying energy, the energy creates new quark-antiquark pairs, producing new particles rather than freeing the original quarks. This property, called confinement, means that quarks exist only inside composite particles. The strong force also binds protons and neutrons together in atomic nuclei. This is sometimes called the residual strong force, a spillover effect from the stronger interactions binding quarks inside the protons and neutrons. Protons in a nucleus are positively charged and electrically repel each other. Without another force to overcome this repulsion, nuclei would fly apart. The strong force provides this binding, but only at very short range. Protons and neutrons must be essentially touching for the strong force to act. This is why large nuclei are unstable. The electrical repulsion between many protons extends across the entire nucleus, but the strong force acts only between neighboring particles. Beyond a certain size, nuclei cannot remain bound. The strong force is approximately 100 times stronger than electromagnetism at the scale of the atomic nucleus. This immense strength is necessary to overcome the electrical repulsion between protons and hold nuclei together. Yet despite its power, the strong force operates over such short distances that it has no noticeable effect on everyday scales. Outside the nucleus, the strong force is essentially negligible. The weak nuclear force is responsible for certain types of radioactive decay. In beta decay, a neutron transforms into a proton, emitting an electron and an antineutrino. This process is mediated by the weak force. The weak force can change the identity of quarks, transforming one type or flavor into another. A down quark can become an up quark, changing a neutron, which contains 2 down quarks and 1 up quark, into a proton, which contains 1 down quark and 2 up quarks. This ability to change quark flavors makes the weak force unique. The strong force and electromagnetism do not change particle identities. They can move particles, accelerate them, bind them together, but they cannot transform a quark of one type into a quark of another type. Only the weak force has this capability. This is why the weak force plays a crucial role in nuclear reactions. In the sun's core, the fusion of hydrogen into helium requires protons to transform into neutrons, a process that can occur only through the weak force. Despite its name, the weak force is not particularly weak compared to gravity. It is weaker than electromagnetism and much weaker than the strong force, but it is vastly stronger than gravity. The weak force operates over even shorter ranges than the strong force, distances smaller than the size of a proton. This extremely short range makes weak interactions rare, giving the force its name. Particles must approach each other extraordinarily closely for the weak force to act. The weak force is mediated by massive particles called W and Z bosons, discovered in the early 1980s. These particles have masses about 80 to 90 times the mass of a proton, making them extremely heavy by particle physics standards. The large masses of these force carriers explain the short range of the weak force. According to quantum field theory, The range of a force is inversely related to the mass of the particle mediating it. Massless photons give electromagnetism infinite range. Massive W and Z bosons confine the weak force to subatomic distances. Gravity is the most familiar force, the one we experience constantly, pulling us toward the Earth, keeping our planet in orbit around the Sun, holding galaxies together. Yet gravity is by far the weakest of the four fundamental forces. It is so weak compared to the others that it is almost negligible at the atomic scale. Consider a hydrogen atom, a single proton with a single electron orbiting it. The electrical attraction between the positive proton and negative electron is what holds the atom together. The gravitational attraction between them is about 10 to the 36th power times weaker. Gravity contributes essentially nothing to the atom's structure. The electromagnetic force completely dominates. You can easily demonstrate gravity's weakness. A small refrigerator magnet can pick up a paperclip, overcoming the gravitational pull of the entire Earth. The magnetic force from a tiny magnet defeats the gravity of a planet containing 6 trillion kilograms of mass. This illustrates how much weaker gravity is than electromagnetism. Why then is gravity so important in shaping the universe? The answer lies in its unique properties. Gravity is always attractive. Every mass attracts every other mass. There are no negative gravitational charges to cancel out positive ones. In contrast, electromagnetism involves both positive and negative charges. On large scales, matter is electrically neutral. Positive and negative charges balance, and electromagnetic forces cancel out. But gravitational effects add up. A planet's gravity is the sum of the gravitational attraction from every atom it contains. The more mass, the stronger the gravity. This allows gravity to dominate at astronomical scales, even though it is incredibly weak. The weakness of gravity compared to other forces is known as the hierarchy problem. Why is gravity so much weaker? We do not have a satisfying answer. Some theories propose that gravity is weak because it extends into extra dimensions beyond the 3 spatial dimensions we experience. Gravity spreads out into these extra dimensions, diluting its strength in our familiar 3-dimensional space. These theories remain speculative, awaiting experimental confirmation. Empty space is not truly empty. It is filled with an invisible energy field called the Higgs field, permeating every point in the universe. This field is fundamental to how particles acquire mass. Before the Higgs field was understood, physicists had a problem. The equations describing fundamental forces in particles worked best if particles had no mass. But obviously, most particles do have mass. Electrons, quarks, and W and Z bosons all have mass. Where does this mass come from? The answer is the Higgs field. Particles interact with this field as they move through space. The strength of the interaction determines how much mass the particle has. Particles that interact strongly with the Higgs field, like the top quark, have large masses. Particles that interact weakly, like electrons, have small masses. Particles that do not interact at all, like photons, remain massless. You can think of the Higgs field as resembling a thick syrup-filling space. Particles moving through the syrup experience resistance. The more they interact with the syrup, the harder it is for them to accelerate, which is equivalent to having more mass. Some particles pass through the syrup easily, others struggle against it. This resistance to acceleration is what we call mass. The existence of the Higgs field was proposed in the 1960s by several physicists, including Peter Higgs, but experimental confirmation took decades. If the Higgs field exists, its quantum excitations should manifest as a particle called the Higgs boson. Finding this particle required building the most powerful particle accelerator ever constructed, the Large Hadron Collider at CERN. In 2012, scientists announced the discovery of a particle consistent with the Higgs boson, confirming the existence of the Higgs field and completing the standard model of particle physics. Higgs and François Englert received the Nobel Prize in Physics in 2013. The discovery of the Higgs boson was a triumph for theoretical physics. The particle's properties matched predictions made decades earlier, based purely on mathematical consistency and symmetry principles. The Higgs field is now understood as a fundamental component of the universe, as essential as space and time themselves. Forces between particles are not transmitted by magical action at a distance. According to quantum field theory, forces arise from the exchange of particles called force carriers or gauge bosons. Each fundamental force has associated particles that mediate the interaction. The electromagnetic force is mediated by photons. When two charged particles interact electromagnetically, they exchange virtual photons. These are not the same as the real photons that make up light beams. Virtual photons exist only briefly, popping into and out of existence in accordance with quantum uncertainty. They are the messengers carrying the electromagnetic force from one charged particle to another. An electron creates an electromagnetic field by continuously emitting and absorbing virtual photons. Another charged particle nearby absorbs some of these virtual photons, feeling a force. If the particles have like charges, the exchange produces repulsion. If they have opposite charges, the exchange produces attraction. The mathematics of quantum electrodynamics, or QED, describes these interactions with extraordinary precision. QED is the most accurately tested theory in all of science, with predictions matching experiments to better than 1 part in a billion. Photons themselves are electrically neutral. They do not feel the electromagnetic force. This is why light beams pass through each other without interacting. Photons do not scatter off other photons, at least not in ordinary circumstances. This property simplifies the mathematics of electromagnetism considerably. The strong force is mediated by particles called gluons. Just as photons carry the electromagnetic force between charged particles, gluons carry the strong force between quarks. But gluons have a crucial difference from photons. Gluons themselves carry a type of charge associated with the strong force called color charge. This means gluons interact with each other. They feel the strong force. This self-interaction has profound consequences. When you try to separate two quarks, you stretch the gluon field connecting them. Unlike electromagnetic field lines, which spread out and weaken with distance, the gluon field lines remain tightly bundled, forming a narrow tube of strong force field between the quarks. The energy in this tube increases with distance. Eventually, there is enough energy in the tube to create a new quark-antiquark pair, which splits the tube into two separate pieces. You end up with two bound quark systems instead of two free quarks. This is why quarks are confined and can never be isolated. The behavior of the strong force at different distances is unusual. At very short distances, quarks inside a proton barely interact. They behave almost as if they are free particles. This is called asymptotic freedom. At larger distances, comparable to the size of a proton, the strong force grows dramatically stronger, confining the quarks. This distance-dependent behavior is opposite to electromagnetism, which grows weaker at larger distances. Understanding the strong force and quark confinement required decades of theoretical and experimental work, culminating in quantum chromodynamics, or QCD, the theory of the strong interaction. Gluons come in 8 types, reflecting the mathematical structure of the color charge. Quarks carry one of 3 color charges, conventionally called red, green, and blue, though these have nothing to do with actual colors. These are just labels for the different types of strong force charge. Bound states of quarks, like protons and neutrons, are always color neutral. containing one quark of each color, or a quark and antiquark of opposite colors. This ensures that composite particles do not carry color charge and interact only through the weaker residual strong force. Physics suggests that space and time are not infinitely divisible. There is a smallest meaningful length scale, below which our concepts of distance and time break down. This is the Planck length, approximately 1.6 times 10 to the negative 35 meters. It is unimaginably small, about 10 to the negative 20 times smaller than a proton, itself already unimaginably small. The Planck length emerges naturally when you combine the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. At this scale, quantum fluctuations in spacetime become so violent that the smooth geometry described by general relativity no longer makes sense. Space and time themselves become granular, foamy, uncertain. Below the Planck length, we expect that quantum effects of gravity become dominant. We would need a theory of quantum gravity to describe physics at these scales, a theory we do not yet have. General relativity describes gravity but is not quantum mechanical. Quantum field theory describes the other three forces but does not include gravity. These two frameworks are incompatible at the deepest level. At the Planck scale, their incompatibility becomes unavoidable. Similarly, there is a Planck time, about 5.4 times 10 to the negative 44 seconds, the time it takes light to travel one Planck length. We cannot meaningfully discuss events shorter than the Planck time. There is also a Planck energy and a Planck mass. These represent scales where quantum gravity effects dominate. No particle accelerator will ever reach these energies. They are beyond the realm of direct experimental access, but the Planck scale represents the ultimate limit of physics, the boundary where our current theories fail and new physics must emerge. The Standard Model of particle physics successfully describes the electromagnetic, weak, and strong forces and all known elementary particles. It has been tested extensively and has passed every test. Yet physicists believe it is not the final theory. It has unexplained features and does not include gravity. Many extensions and modifications have been proposed. One of the most elegant proposals is supersymmetry, often called SUSY. This theory posits that every known particle has a partner particle with different spin. Fermions, particles with half-integer spin like electrons and quarks, would have bosonic partners with integer spin. Bosons, particles with integer spin, like photons and gluons, would have fermionic partners with half-integer spin. The electron would have a partner called the selectron. The quark would have a squark. The photon would have a photino. The complete theory predicts a whole zoo of superpartner particles. Supersymmetry has appealing theoretical properties. It solves certain mathematical problems in particle physics, stabilizes the Higgs boson mass, and provides a natural candidate for dark matter. The lightest supersymmetric particle would be stable and electrically neutral, fitting the profile of dark matter perfectly. Supersymmetry also brings us closer to unifying the fundamental forces. However, despite extensive searches at particle accelerators, including the Large Hadron Collider, no superpartner particles have been found. If they exist, they must be heavier than expected, requiring even more powerful accelerators to discover. Some physicists remain optimistic that supersymmetry will eventually be confirmed. Others suspect that nature has chosen a different path. The absence of supersymmetric particles is one of the major puzzles in contemporary physics. The four fundamental forces appear very different, but physicists have long suspected they are manifestations of a single, more fundamental force. At high energies, the distinctions between forces blur. In the 1960s and 70s, physicists developed the electroweak theory, which unifies electromagnetism and the weak force into a single electroweak interaction. At low energies, this symmetry is broken and the forces appear distinct. But at energies above about 100 giga-electron-volts, achieved in particle accelerators, the electromagnetic and weak forces merge into the electroweak force. The next step would be a grand unified theory, or GUT, that unifies the electroweak and strong forces. Such theories predict that at extremely high energies, around 10 to the 16th giga-electron-volts, all three forces have equal strength and are described by a single unified force. At lower energies, this unified force breaks into the three separate forces we observe. Grand unified theories make testable predictions. Most predict that protons are not absolutely stable, but decay very slowly, with lifetimes of perhaps 10 to the 34 years. Experiments have searched for proton decay in large underground detectors containing thousands of tons of ultra-pure water, watching for the flash of light that would signal a proton decaying. So far, no decays have been observed, placing limits on proton lifetime that rule out the simplest grand unified theories. More complex versions remain possible. The ultimate goal is a theory of everything that would unify all four forces, including gravity. This requires a theory of quantum gravity. The leading candidates are string theory, which proposes that fundamental particles are tiny vibrating strings in a higher dimensional spacetime, and loop quantum gravity, which quantizes spacetime itself. Neither theory is complete or experimentally confirmed. The quest for a theory of everything remains one of the grandest challenges in physics. The universe operates through four fundamental forces: gravity, electromagnetism, the strong force, and the weak force. The strong force binds quarks and nuclei with immense power. The weak force enables radioactive decay and changes quark flavors. Gravity, though incredibly weak, dominates at cosmic scales. The Higgs field gives particles mass through their interactions with it. Photons mediate electromagnetism. Gluons mediate the strong force and interact with themselves. The Planck length marks the scale where quantum gravity becomes important. Supersymmetry proposes partner particles for all known particles, though none have been found. Grand unified theories seek to unify the electromagnetic, weak, and strong forces. These forces and fields form the foundation of reality. Every phenomenon, from the quantum foam of space-time to the motion of galaxies, arises from their interplay. Understanding these forces represents humanity's deepest insight into the workings of nature, the culmination of centuries of observation, experiment, and mathematical reasoning. Light surrounds us, illuminates our world, carries information from distant stars to our eyes. Yet what we call light, the rainbow of colors visible to human eyes, represents only a narrow sliver of a vast spectrum of electromagnetic radiation that fills the universe. From the longest radio waves spanning kilometers to the shortest gamma rays smaller than atomic nuclei, electromagnetic radiation comes in an enormous range of wavelengths and energies. Tonight, we explore light and radiation in all its forms, from the familiar to the exotic, from the photons streaming from the sun to the most energetic events in the cosmos. Light is a wave of oscillating electric and magnetic fields propagating through space. These fields are perpendicular to each other and to the direction of travel. As the wave moves, the electric field oscillates up and down while the magnetic field oscillates side to side, and the wave carries energy forward. This is electromagnetic radiation, and it requires no medium to travel. Unlike sound waves, which need air or water to propagate, light waves travel perfectly well through the vacuum of space. The electromagnetic spectrum is defined by wavelength or frequency. These are inversely related. Long wavelength corresponds to low frequency and low energy. Short wavelength corresponds to high frequency and high energy. Radio waves have wavelengths ranging from millimeters to kilometers. They carry relatively little energy, but can travel great distances and pass through many materials. We use them for communication, broadcasting signals across the planet, and into space. Microwaves have wavelengths from about 1 millimeter to 1 meter. They are absorbed by water molecules, causing them to vibrate and heat up. This is how microwave ovens work. Microwaves are also used for radar and satellite communication. The cosmic microwave background, the afterglow of the Big Bang, is electromagnetic radiation that has been stretched by cosmic expansion from visible light to microwaves. Infrared radiation has wavelengths from about 700 nanometers to 1 millimeter, just beyond the red end of the visible spectrum. Warm objects emit infrared. You radiate infrared continuously. Night vision devices detect infrared to see in darkness. Infrared astronomy observes cool objects like dust, clouds, and forming stars that emit strongly in infrared but are invisible light visible. Light spans wavelengths from roughly 400 to 700 nanometers. Human eyes have evolved to detect this narrow range because it happens to be where the sun emits most strongly and where Earth's atmosphere is most transparent. Red light has the longest wavelengths in the visible range, around 700 nanometers. Violet light has the shortest, around 400 nanometers. The colors of the rainbow represent different wavelengths within this tiny window. Ultraviolet radiation has wavelengths from about 10 to 400 nanometers, shorter than violet light. The sun emits significant ultraviolet, but Earth's ozone layer absorbs most of it, protecting life from its damaging effects. Ultraviolet can damage DNA, causing mutations and cancer. However, some ultraviolet is essential for synthesizing vitamin D in skin. Ultraviolet astronomy reveals hot stars, active galaxies, and high-energy processes in invisible light. X-rays have wavelengths from about 10 picometers to 10 nanometers. They carry enough energy to ionize atoms and penetrate many materials. Medical X-rays use this penetrating ability to image bones and tissues. X-ray astronomy observes extremely hot gas in galaxy clusters, materials swirling into black holes, and the remains of exploded stars. X-rays are absorbed by Earth's atmosphere, so X-ray telescopes must be placed in space. Gamma rays have the shortest wavelengths, less than 10 picometers, shorter than an atom. They are the most energetic form of electromagnetic radiation. Gamma rays are produced by radioactive decay, nuclear reactions, and the most violent events in the universe. They can damage living tissue, destroying cells and breaking DNA. But they also reveal physics at the highest energies, probing processes that cannot be recreated on Earth. All electromagnetic radiation travels at the same speed in vacuum, the speed of light, approximately 300 million meters per second. This is not just the speed at which light happens to travel. It is a fundamental constant of nature, woven into the structure of space-time itself. The speed of light appears in Einstein's equations of relativity. It determines how electric and magnetic fields relate to each other. It sets the maximum rate at which information can propagate from one place to another. Nothing with mass can reach the speed of light. As an object accelerates, its energy increases. As it approaches light speed, more and more energy is required to accelerate it further. To actually reach light speed would require infinite energy. Light itself can travel at this speed only because photons have no mass. Any massless particle must travel at exactly the speed of light. It cannot travel slower or faster. The constancy of light speed leads to the relativistic effects of time dilation and length contraction. It means that cause and effect are protected. If information could travel faster than light, it would be possible to send signals backward in time, creating paradoxes. The speed of light is the universe's way of maintaining causality, ensuring that effects follow causes in all reference frames. Attempts to circumvent this limit through wormholes or warp drives remain purely theoretical and face enormous, perhaps insurmountable obstacles. For now and the foreseeable future, the speed of light remains an absolute barrier, limiting how quickly we can communicate with distant spacecraft and constraining how quickly we could travel to other stars. General relativity predicts that massive objects curve space-time, and light follows the curvature. When light from a distant object passes close to a massive foreground object, like a galaxy or galaxy cluster, the light's path bends. This is gravitational lensing. The massive object acts as a cosmic lens, bending and focusing the light. Gravitational lensing can magnify distant objects, making them appear brighter and larger than they would otherwise. It can create multiple images of the same object, as light takes different paths around the lens to reach us. It can distort images into arcs or even complete rings, called Einstein rings. These effects allow astronomers to observe objects that would otherwise be too faint to detect, and to map the distribution of mass in the lensing object, including dark matter. Strong gravitational lensing produces dramatic multiple images and large distortions. Weak gravitational lensing produces subtle distortions in the shapes of background galaxies, detectable only statistically across many galaxies. By measuring these distortions, astronomers can map dark matter on cosmic scales, revealing the hidden scaffolding of the universe. Gravitational lensing has become a powerful tool in astronomy. It has been used to discover distant galaxies, to weigh galaxy clusters, to map dark matter, and to search for planets around other stars through a technique called microlensing. When a foreground star passes in front of a more distant star, the gravity of the foreground star magnifies the background star's light. If the foreground star has planets, they create additional brief spikes in the brightness, revealing their presence. Einstein predicted gravitational lensing in 1915. But the first example was not observed until 1979, when astronomers found two quasars with identical spectra and redshifts in almost the same location on the sky. They were not two separate quasars, but two images of the same quasar, gravitationally lensed by an intervening galaxy. Nothing can travel faster than light in vacuum, but light itself slows down when passing through matter. In water, light travels at about 3/4 of its vacuum speed, in glass about 2/3. This slowing occurs because photons are constantly absorbed and re-emitted by atoms in the material, and the process takes time. When a charged particle, like an electron, travels through a transparent medium faster than light travels in that medium, something remarkable happens. The particle emits a cone of light called Cherenkov radiation. This is analogous to the sonic boom produced by an object traveling faster than sound. As the particle moves through the medium faster than light can, it creates a shockwave of electromagnetic radiation. Cherenkov radiation appears as a characteristic blue glow. It is visible in the water surrounding nuclear reactors, produced by high-energy particles emitted from the reactor core. These particles are traveling faster than light travels in water, generating the blue glow. Cherenkov radiation is not just a curiosity. It is used in particle detectors to identify and measure high-energy particles. When a neutrino interacts with water, it can create a charged particle that emits Cherenkov light, allowing the neutrino to be detected indirectly. Large underground neutrino detectors consist of thousands of tons of ultra-pure water surrounded by sensitive light detectors. When a neutrino from the sun, a supernova, or a cosmic ray interaction passes through the water and interacts with an atomic nucleus, the resulting charged particle produces a flash of Cherenkov light. By measuring the pattern and timing of this light, scientists can determine the energy and direction of the original neutrino. The beautiful blue glow of Cherenkov radiation reveals the presence of high-energy particles otherwise invisible. It has become an essential tool for studying neutrinos, cosmic rays, and fundamental particle interactions. When charged particles are accelerated by magnetic fields to speeds approaching the speed of light, they emit intense electromagnetic radiation called synchrotron radiation. This occurs in particle accelerators on Earth and in natural astrophysical environments where cosmic magnetic fields accelerate particles. As a charged particle curves through a magnetic field, it accelerates. Accelerating charges emit electromagnetic radiation. At low speeds, this radiation is relatively weak and isotropic, but as particles approach light speed, the radiation becomes intense and highly beamed in the forward direction. The faster the particle moves, the more tightly focused the beam becomes. Synchrotron radiation from relativistic particles is extremely bright and covers a broad range of wavelengths. Many astronomical objects emit synchrotron radiation. Supernova remnants, where shock waves accelerate particles to near light speed, glow in synchrotron radiation. Jets from active galactic nuclei and pulsars emit synchrotron radiation as particles stream along magnetic field lines at relativistic speeds. By studying the spectrum and polarization of synchrotron radiation, astronomers can determine the strength of magnetic fields and the energy distribution of particles in distant objects. On Earth, scientists use synchrotron radiation from particle accelerators as a powerful research tool. Synchrotron light sources accelerate electrons to near light speed and bend their paths using magnets, causing them to emit intense, tunable beams of X-rays and ultraviolet. These beams are used for studying the atomic structure of materials, imaging biological molecules, and probing chemical reactions. Dozens of synchrotron facilities around the world serve researchers from diverse fields. The most energetic electromagnetic events observed in the universe are gamma-ray bursts. These are brief flashes of gamma rays, lasting from milliseconds to minutes, releasing enormous amounts of energy. A typical gamma-ray burst releases more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. For the brief duration of the burst, the gamma-ray source can outshine everything else in the gamma-ray sky combined. Gamma-ray bursts were discovered accidentally in the late 1960s by military satellites designed to detect nuclear weapons tests. The satellites detected flashes of gamma rays coming from space rather than Earth, leading to one of the great mysteries in astrophysics. For decades, the origin of gamma-ray bursts remained unclear. We now understand that there are two main types of gamma-ray bursts. Long-duration bursts, lasting more than 2 seconds, are associated with the collapse of massive stars into black holes. As the core collapses, jets of material are launched at nearly the speed of light. These jets punch through the star and emit gamma rays. We sometimes see these events as supernovae as well. Short-duration bursts, lasting less than 2 seconds, are produced by the merger of two neutron stars, or a neutron star and a black hole. The merger creates jets that produce the gamma-ray emission. Gamma-ray bursts are extremely distant. Most occur in galaxies billions of light-years away. The fact that we can detect them at such distances indicates how energetic they are. If a gamma-ray burst occurred within our own galaxy, pointed toward Earth, it could be catastrophic for life, stripping away the ozone layer and bathing the planet in deadly radiation. Fortunately, such events are rare, and the beaming effect means only objects nearly aligned with the jet see the gamma rays. Detecting gamma-ray bursts requires satellites. Since Earth's atmosphere blocks gamma rays, observatories like Swift and Fermi constantly scan the sky, detecting several gamma-ray bursts per week. When a burst is detected, its position is immediately transmitted to ground-based telescopes, which observe the fading afterglow in optical, infrared, and radio wavelengths. These multi-wavelength observations have revealed the nature of gamma-ray bursts and the extreme physics occurring in these events. Among the most extreme objects in the universe are magnetars, a type of neutron star with magnetic fields of unimaginable strength. Typical neutron stars have magnetic fields trillions of times stronger than Earth's. Magnetars have fields another 1,000 times stronger still, reaching 10 to the 15th Gauss or more. These are the strongest magnetic fields known in the universe. The magnetic field of a magnetar is so intense that it warps the structure of space itself near the star. Atoms stretched in the field become elongated like needles. The vacuum between atoms becomes birefringent, splitting light into different polarizations like a crystal. At distances of 1,000 kilometers from a magnetar, the magnetic field is strong enough to disrupt molecular bonds and biological tissue. A magnetar halfway to the moon would erase every magnetic storage device on Earth, wiping out credit cards, hard drives, and any other magnetically stored data. Magnetars are relatively young neutron stars, typically less than 10,000 years old. They are formed with enormous rotation rates and intense magnetic fields, possibly amplified by dynamo effects during their formation. The decay and reconfiguration of these powerful magnetic fields releases enormous energy. Magnetars occasionally undergo starquakes, sudden cracks in their solid crust caused by magnetic stresses. These starquakes release bursts of X-rays and gamma rays detectable across the galaxy. 1. Magnetar outburst in December 2004 was so intense that it saturated detectors on satellites throughout the solar system and affected Earth's upper atmosphere. Despite the magnetar being 50,000 light-years away, the burst lasted only a fraction of a second, but released more energy than the Sun emits in 150,000 years. Such events, though rare, demonstrate the extreme energies involved in magnetar physics. Only a few dozen magnetars are known in our galaxy. They are difficult to find because they are small, about 20 kilometers in diameter, and most are relatively dim in visible light. They reveal themselves through their X-ray and gamma-ray emission. Studying magnetars helps physicists understand how matter behaves in the most extreme magnetic fields possible, conditions that cannot be recreated in any laboratory. The brightest continuously shining objects in the universe are quasars, the intensely luminous cores of distant active galaxies. The term quasar is short for quasi-stellar radio source, named because they appeared point-like, similar to stars, but emitted powerful radio waves unlike any known stars. Observations revealed they were extraordinarily distant and luminous, outshining entire galaxies while being no larger than the solar system. Quasars are powered by supermassive black holes at the centers of galaxies. Material from the surrounding galaxy falls toward the black hole, forming a swirling accretion disk. Friction in the disk heats the material to millions of degrees, causing it to emit intense radiation across the electromagnetic spectrum. The gravitational energy released as matter falls into the black hole powers the quasar's luminosity, making it one of the most efficient energy generation mechanisms in the universe. A typical quasar can emit the light of 1 trillion suns from a region smaller than our solar system. The brightest quasars are visible across billions of light-years. Most quasars are seen at great distances, meaning we observe them as they were long ago, when the universe was young. Quasar activity was much more common in the early universe than today. Galaxies in the current era have generally exhausted the gas supplies near their central black holes, and their quasars have faded. Our own Milky Way galaxy almost certainly hosted a bright quasar phase early in its history, when gas was abundant near the central supermassive black hole. Today, the Milky Way's central black hole is relatively quiet, accreting little material and emitting faint radiation. But occasionally, stars or gas clouds venture too close and are torn apart, causing brief flares of activity. Quasars serve as cosmic lighthouses, visible across most of the universe. By studying how quasar light is absorbed by intervening gas clouds, astronomers map the distribution of matter between us and the quasar, tracing the history of cosmic structure formation. Quasars also serve as distant markers for measuring the expansion of the universe and searching for gravitational wave backgrounds. Through timing variations in their brightness, space is filled with high energy, particles traveling at nearly the speed of light. These cosmic rays are mostly protons, along with some heavier atomic nuclei, electrons and positrons. They constantly bombard Earth from all directions, striking the upper atmosphere and creating showers of secondary particles that reach the ground. Every second, several cosmic rays pass through your body. Most cosmic rays have relatively modest energies, but some have extraordinary energies, far beyond anything achievable in particle accelerators. The highest energy cosmic ray ever detected, observed in 1991, carried about 50 joules of energy, equivalent to the kinetic energy of a baseball thrown at 100 kilometers per hour, but concentrated in a single subatomic particle. Such ultra-high energy cosmic rays are exceedingly rare, with only a handful detected over decades of observations. the origin of cosmic rays remains not fully understood. Lower energy cosmic rays are likely accelerated by supernova shock waves in our galaxy. As the expanding shell of gas from a supernova plows through the interstellar medium, it creates a shock wave that can accelerate particles to high energies. But this mechanism probably cannot explain the highest energy cosmic rays. These particles have energy so high that they must originate outside our galaxy, perhaps from the jets of active galactic nuclei, from gamma-ray bursts, or from other exotic sources. Ultra-high energy cosmic rays present a mystery. According to theory, they should not be able to reach us from very distant sources. As they travel through space, they interact with the cosmic microwave background, losing energy in a process called the GZK cutoff, after the physicists who predicted it. Protons with energies above a certain threshold should travel only limited distances before losing enough energy to fall below that threshold. Yet we detect cosmic rays above this threshold, implying they must originate relatively nearby, cosmically speaking, within perhaps a few 100 million light-years. Large detector arrays covering many square kilometers monitor cosmic rays by detecting the particle showers they create in the atmosphere. The Pierre Auger Observatory in Argentina, covering 3,000 square kilometers, uses arrays of water tanks and fluorescence detectors to study ultra-high energy cosmic rays. By analyzing the shower patterns, scientists can determine the energy and approximate direction of the incoming cosmic ray, searching for sources and studying particle physics at energies unattainable in accelerators. Neutrinos are ghostly particles that barely interact with matter. Trillions of neutrinos from the Sun pass through you every second without any effect. Neutrinos come in 3 types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos, named after the charged particles they are associated with. For decades, neutrinos were thought to be massless, traveling at the speed of light like photons. But observations revealed a mystery. Experiments detected only about 1/3 as many electron neutrinos from the Sun as predicted by solar models. This was the solar neutrino problem. Where were the missing neutrinos? The solution turned out to revolutionize particle physics. Neutrinos can change flavor as they travel. Electron neutrinos produced in the Sun's core transform into muon and tau neutrinos on their way to Earth. Early detectors were sensitive only to electron neutrinos, so they missed 2/3 of the neutrinos. This flavor oscillation is possible only if neutrinos have mass. Massless particles cannot change identity. The discovery of neutrino oscillation proved that neutrinos have mass, though very small, millions of times lighter than electrons. This was the first evidence for physics beyond the Standard Model, which assumes massless neutrinos. The discovery earned the Nobel Prize in Physics in 2015. Neutrino oscillation occurs because the 3 neutrino flavors we observe are not the same as the 3 neutrino mass states, the eigenstates that have definite masses. A neutrino produced as an electron, neutrino is actually a quantum superposition of 3 mass states. As the neutrino travels, the different mass components accumulate different quantum phases, causing the superposition to evolve. At different points along its path, measuring the neutrino might reveal it as an electron neutrino, a muon neutrino, or a tau neutrino. The probability of finding each flavor oscillates periodically. The oscillation frequency depends on the differences in neutrino masses and the neutrino's energy. By measuring oscillations, physicists determine these mass differences, though the absolute masses remain unknown. Neutrino mass has implications for cosmology, affecting structure formation in the early universe and contributing to the total mass budget of the cosmos. Understanding neutrinos is essential for a complete picture of fundamental physics. The universe is filled with electromagnetic radiation in all its forms, from radio waves to gamma rays. Light travels at the ultimate cosmic speed limit. Massive objects can bend light's path through gravitational lensing. Charged particles moving faster than light in a medium emit Cherenkov radiation. Particles accelerated by magnetic fields emit synchrotron radiation. Gamma-ray bursts release enormous energies in brief flashes. Magnetas possess the strongest magnetic fields in the universe. Quasars shine with the light of trillions of suns, powered by supermassive black holes. Cosmic rays bombard us constantly, their origin not fully understood, and neutrinos oscillate between flavors, proving they have mass. These phenomena reveal the richness and diversity of the cosmos. Light is not merely illumination, but a messenger, carrying information across space and time. Radiation in all its forms allows us to observe the universe, from the cosmic microwave background echoing the Big Bang to gamma rays from the most violent events occurring today. Every wavelength reveals different physics, different objects, different processes. Our solar system is a complex gravitational dance, a collection of worlds bound together by the sun's gravity, each following its own path through space according to precise mathematical laws. From the scorching surface of Mercury to the frozen reaches beyond Neptune, each planet, moon, and small body tells a story of formation, evolution, and ongoing physical processes. Tonight, we explore the mechanics and mysteries of our cosmic neighborhood, from the nuclear furnace at the sun's heart to the subtle gravitational effects that shape planetary orbits. At the center of our solar system burns a star, the sun, a sphere of plasma held together by its own gravity and powered by nuclear fusion in its core. The core is an unimaginably hostile environment, with temperatures reaching approximately 15 million degrees Celsius and pressures millions of times greater than Earth's atmospheric pressure. These extreme conditions are necessary for nuclear fusion to occur. In the sun's core, hydrogen nuclei, which are simply protons, collide with such energy that they overcome their mutual electrical repulsion and fuse together. Through a series of reactions called the proton-proton chain, 4 hydrogen nuclei eventually combine to form one helium nucleus. The helium nucleus has slightly less mass than the 4 hydrogen nuclei that formed it. The missing mass has been converted to energy, released as gamma-ray photons and neutrinos according to Einstein's equation. Energy equals mass times the speed of light squared. The energy released in the core begins a long journey to the surface. Gamma-ray photons emitted by fusion reactions are immediately absorbed by the dense plasma and re-emitted in random directions. Each photon takes countless tiny steps, being absorbed and re-emitted over and over, gradually working its way outward. The journey from core to surface takes roughly 100,000 to 1 million years. By the time the energy reaches the surface, the high-energy gamma rays have been converted through countless interactions into lower-energy visible light and infrared radiation. The sun's surface, called the photosphere, has a temperature of about 5,500 degrees Celsius. This is where the sun becomes transparent enough for photons to escape into space. The light streaming from the sun's surface carries the energy generated by fusion deep in the core, energy that sustains all life on Earth and drives the dynamics of our entire solar system. The sun converts approximately 600 million tons of hydrogen into helium every second, releasing energy equivalent to trillions of nuclear bombs. It has been doing this for about 4.6 billion years and will continue for roughly another 5 billion years before exhausting the hydrogen in its core. The sun is middle-aged, a stable, reliable star that provides the steady energy flow necessary for complex life to evolve. Mercury, the closest planet to the sun, moves through a stronger gravitational field than any other planet. Its orbit is noticeably elliptical, bringing it as close as 46 million kilometers to the sun at perihelion and as far as 70 million kilometers at aphelion. According to Newton's law of gravitation, Mercury's orbit should be a fixed ellipse, slowly rotating due to perturbations from other planets, precessing at a rate calculable from Newtonian mechanics. Observations in the 19th century revealed that Mercury's orbit precesses slightly faster than Newton's theory predicts. The point of closest approach to the Sun, the perihelion, shifts by about 5,600 arc-seconds per century. Most of this precession, about 5,027 arc-seconds, can be explained by the gravitational influence of other planets, but 43 arcseconds per century remained unexplained. This tiny discrepancy puzzled astronomers for decades. In 1915, Einstein published his theory of general relativity, which describes gravity not as a force, but as the curvature of space-time caused by mass and energy. General relativity predicts that orbits in curved space-time should behave slightly differently than Newton's theory predicts, especially in strong gravitational fields close to massive objects. When Einstein applied his equations to Mercury's orbit, the theory predicted an additional precession of exactly 43 arcseconds per century, precisely matching the unexplained observation. This was one of the first confirmations of general relativity and a triumph for Einstein. The theory explained a long-standing astronomical puzzle with no adjustable parameters, demonstrating that general relativity provides a more accurate description of gravity than Newton's theory, particularly in strong gravitational fields. Mercury's anomalous precession became a classic test of general relativity, one that the theory passed perfectly. Modern tests using radar ranging and spacecraft tracking have measured Mercury's precession with extraordinary precision, confirming general relativity to within a fraction of a percent. The same relativistic effects occur for all planets, but they are largest for Mercury because it orbits closest to the Sun where space-time curvature is strongest. When a spacecraft approaches a planet on the right trajectory, it can use the planet's gravity to change speed and direction without expending fuel. This gravitational slingshot, or gravity assist, is a cornerstone of modern space exploration, allowing missions to reach distant destinations that would otherwise be impossible with available rocket technology. The mechanics of a gravity assist are subtle. From the planet's reference frame, the spacecraft approaches, swings around, and departs with the same speed it arrived, just in a different direction. Its kinetic energy relative to the planet is unchanged, but the planet is moving through space, orbiting the Sun. From the Sun's reference frame, if the spacecraft approaches the planet from behind, moving in the same direction the planet is moving, it can be accelerated. The spacecraft effectively steals a tiny amount of the planet's orbital momentum and energy. Conversely, if the spacecraft approaches from the front, meeting the planet head-on, it loses speed relative to the Sun. The planet gains a tiny amount of momentum, though the effect on the planet is immeasurably small due to its enormous mass. These maneuvers allow spacecraft to gain or lose speed without burning fuel, making missions feasible that would otherwise require impossibly large rockets. The Voyager spacecraft used multiple gravity assists, swinging by Jupiter and Saturn to gain enough speed to reach Uranus and Neptune and eventually leave the solar system. The Cassini mission used gravity assists from Venus twice, and then Earth before heading to Jupiter for a final boost towards Saturn. The Parker Solar Probe uses repeated Venus flybys to gradually lower its orbit closer and closer to the Sun. Calculating gravity assist trajectories requires precise knowledge of orbital mechanics and careful mission planning. The spacecraft must arrive at exactly the right time and place for the planet to be in the correct position. These opportunities occur only at specific intervals when planetary alignments are favorable, which is why certain missions can only launch during narrow windows that occur every few years or decades. In a system where two large bodies orbit each other, their combined gravitational fields create 5 special points called Lagrange points, where a smaller object can maintain a stable position relative to the two larger bodies. These points, named after the mathematician Joseph Louis Lagrange, who discovered them in 1772, have become important locations for spacecraft and satellites. The 5 Lagrange points are designated L1 through L5. The L1 point lies between the two bodies, where the gravitational pulls and centrifugal force balance. For the Earth-Sun system, L1 is about 1.5 million kilometers from Earth toward the Sun. Satellites at L1 have an unobstructed view of the Sun, making this an ideal location for solar observation spacecraft, like the Solar and Heliospheric Observatory. The L2 point lies beyond the smaller body, away from the larger one, at the same distance as L1 but on the opposite side. For Earth's Sun L2, also about 1.5 million kilometers from Earth but away from the Sun, the Earth blocks sunlight, making it an excellent location for space telescopes that need to stay cool. The James Webb Space Telescope orbits the Earth-Sun L2 point, where it can observe the universe in infrared without interference from Earth, Moon, or Sun. The L3 point lies on the opposite side of the larger body from the smaller one. For the Earth-Sun system, L3 is on the far side of the Sun from Earth. It has little practical use because the Sun blocks communication. With anything positioned there, the L4 and L5 points form equilateral triangles with the two bodies, 60 degrees ahead and behind the smaller body in its orbit. These are the only truly stable Lagrange points. Objects placed at L4 or L5 tend to stay there without active station keeping. Many asteroids cluster at the L4 and L5 points of Jupiter's orbit around the Sun, called Trojan asteroids. Similar collections exist at the L4 and L5 points of other planets. Lagrange points are not single precise locations, but rather regions where objects can orbit in complex patterns called halo orbits or Lissajous orbits. Spacecraft at Lagrange points typically perform small periodic maneuvers to maintain their positions, as they are perturbed by solar radiation pressure and the gravitational influence of other bodies. Our Moon always shows the same face to Earth. No matter where or when you observe the Moon, you see the same craters, the same Maria or dark plains, the same features. The far side of the Moon, often incorrectly called the dark side, remained unseen by human eyes until spacecraft photographed it in 1959. This phenomenon, where one body always keeps the same face toward another, is called tidal locking. Tidal locking occurs due to gravitational interactions between bodies. The Moon raises tides on Earth, two bulges of water on opposite sides of the planet. Similarly, Earth's gravity creates tidal bulges in the Moon. Early in the Moon's history, it rotated faster than it does today, but the tidal bulges created by Earth's gravity are not perfectly aligned with the Earth-Moon direction. As the Moon rotates, these bulges shift position, and Earth's gravity pulls on them, creating a torque that slows the Moon's rotation. Over millions of years, this tidal braking gradually slowed the Moon's rotation until it matched the Moon's orbital period. At this point, the same side of the Moon always faces Earth. The tidal bulge always points toward Earth, and there is no more torque to change the rotation rate. The Moon is tidally locked, rotating once per orbit, keeping one face perpetually toward Earth. Many moons in the solar system are tidally locked to their planets. All four of Jupiter's large Galilean moons are tidally locked. Saturn's major moons are tidally locked. Most moons orbiting close to their planets become tidally locked relatively quickly on astronomical timescales. Even some planets can become tidally locked. Mercury is in a 3-to-2 spin orbit resonance with the Sun, rotating 3 times for every 2 orbits, a state that is gravitationally stable for Mercury's elliptical orbit. Tidal locking also affects Earth. The Moon's gravity creates tides in Earth's oceans, and the friction of these tides gradually slows Earth's rotation. Days are getting longer by about 2 milliseconds per century. Eventually, billions of years from now, Earth will become tidally locked to the Moon, and both bodies will keep the same faces toward each other, though this will take longer than the remaining lifetime of the Sun. Rocket propulsion seems straightforward. Burning fuel produces thrust, which accelerates the spacecraft. But orbital mechanics reveals a subtle and counterintuitive effect called the Oberth effect. A given amount of fuel produces more useful energy when burned at high velocity, particularly near a gravitational body, than when burned at low velocity or far from massive objects. This seems to violate energy conservation, but it does not. The key is understanding that in orbital mechanics, what matters is not just kinetic energy, but orbital energy, which includes both kinetic and potential energy. When you fire rockets at high speed near a planet, you change your velocity, but because you are already moving fast, the change in kinetic energy is larger than it would be at low speeds. Mathematically, Kinetic energy is 1/2 mass times velocity squared. If you increase velocity by some amount, the change in kinetic energy depends on your starting velocity. Increasing from 10 to 11 units of velocity adds 21 units of energy, but increasing from 100 to 101 adds 201 units of energy. The faster you are moving, the more energetic effect a given velocity change has. The Oberth effect is maximized when burning fuel at periapsis, the closest approach to a gravitational body where orbital velocity is highest. This is why efficient trajectories often involve falling close to a planet or sun, firing engines at high speed near closest approach, and then coasting to the destination. The fuel burned near the planet delivers more energy to the spacecraft's orbit than the same fuel burned elsewhere. Spacecraft mission planners exploit the Oberth effect to minimize fuel requirements. A mission to the outer solar system might first dive close to the sun, burning engines at perihelion where the spacecraft is moving fastest relative to the sun, gaining maximum velocity for a given fuel expenditure. Understanding and exploiting subtle effects like this makes the difference between feasible and infeasible missions. Light carries momentum. When photons strike an object, they impart a tiny push. This radiation pressure is negligible in everyday situations, but becomes significant over long distances in the vacuum of space. A spacecraft can harness radiation pressure using a solar sail, a large reflective surface that catches photons from the sun like a sailboat catches wind. Solar sails must be enormous to generate useful thrust, because the pressure of sunlight is so small, less than 10 micronewtons per square meter at Earth's distance from the sun. But in space, even tiny continuous thrust accumulates over time. A solar sail requires no fuel, deriving propulsion entirely from sunlight. This makes it attractive for missions requiring large velocity changes over long durations. Several spacecraft have successfully demonstrated solar sailing. Icaros, launched by Japan in 2010, became the first spacecraft to successfully demonstrate solar sail propulsion in interplanetary space. The Planetary Society's LightSail 2, launched in 2019, demonstrated controlled solar sailing in Earth orbit, using the sail to raise its orbit without expending propellant. Solar sails work best closer to the sun, where sunlight is more intense. Radiation pressure decreases with distance from the sun, limiting the effectiveness of solar sails in the outer solar system. However, near Earth or in the inner solar system, solar sails can achieve significant velocity changes given enough time. Advanced concepts propose using powerful ground-based lasers to propel light sails to relativistic speeds. By focusing intense laser light on a small, highly reflective sail, much more momentum can be delivered than from sunlight alone. Such systems could potentially accelerate tiny probes to a significant fraction of light speed, enabling interstellar missions within human lifetimes. Projects like Breakthrough Starshot are exploring this concept, though enormous technical challenges remain. Saturn is the second largest planet in the solar system, with a radius about 9 times Earth's. It is famous for its spectacular ring system, but it has another remarkable property. Saturn is the least dense planet in the solar system, with an average density of only 0.687 grams per cubic centimeter. For comparison, Earth's density is 5.5 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. Saturn's low density means it would float if you could find a bathtub large enough to hold it. This is sometimes stated as a fun fact, though of course no such bathtub exists, and Saturn would actually deform and break apart under Earth's gravity. But the underlying point is valid. Saturn is composed mostly of hydrogen and helium, the lightest elements. It lacks the rocky core that makes up a substantial fraction of Earth's mass. Saturn's interior structure consists of a relatively small rocky core, perhaps 10 to 20 Earth masses, surrounded by a thick layer of metallic hydrogen, where pressures are high enough to ionize hydrogen atoms, freeing their electrons. Above this lies a layer of liquid molecular hydrogen and helium, transitioning gradually to gaseous hydrogen and helium in the outer atmosphere. This composition, dominated by the lightest elements in the universe, gives Saturn its remarkably low density. Despite its low density, Saturn is massive, about 95 times Earth's mass. This mass generates strong gravity at its cloud tops, about 1.1 times Earth's surface gravity. The planet's rapid rotation, completing one day in just over 10 hours, creates a pronounced equatorial bulge. Saturn's equatorial diameter is about 10% larger than its polar diameter, making it the most oblate planet in the solar system. Saturn's rings, though visually stunning, contribute negligibly to the planet's mass. The rings are composed of countless particles of water ice ranging from dust grains to house-sized boulders, spread in a disk extending hundreds of thousands of kilometers from the planet, but only tens of meters thick in most places. The total mass of the rings is perhaps equivalent to a small moon, tiny compared to Saturn itself. Jupiter, the largest planet in the solar system, has played a crucial role in shaping the solar system and protecting the inner planets, including Earth, from impacts. With a mass more than twice that of all other planets combined, Jupiter's immense gravity influences the orbits of countless comets and asteroids. Jupiter acts as a gravitational shield, deflecting or capturing objects that venture into the inner solar system. Comets on trajectories that would bring them toward Earth can be deflected by Jupiter's gravity, sending them on different paths, perhaps ejecting them from the solar system entirely or sending them into the Sun. Other objects are captured by Jupiter's gravity and either impact the planet or become temporary satellites. In 1994, astronomers observed a dramatic demonstration of Jupiter's protective role when comet Shoemaker-Levy 9 broke apart under Jupiter's tidal forces and impacted the planet in a series of spectacular collisions. Each impact released energy equivalent to millions of nuclear bombs, leaving dark scars in Jupiter's atmosphere visible for months. Had such a comet struck Earth, the results would have been catastrophic. However, Jupiter's role is complex. While it deflects many objects away from the inner solar system, it can also perturb objects from the distant Kuiper Belt and Oort cloud, sending them inward where they might threaten Earth. The overall effect is still protective, reducing the impact rate on Earth compared to what it would be without Jupiter, but the dynamics are more nuanced than a simple shielding effect. Jupiter's gravitational influence also affects the asteroid belt between Mars and Jupiter. Orbital resonances with Jupiter create gaps in the belt called Kirkwood gaps, where few asteroids are found. Asteroids in these resonance locations experience periodic gravitational tugs from Jupiter that gradually alter their orbits, clearing out these regions. Understanding Jupiter's gravitational effects is important for assessing impact hazards to Earth and for understanding the history of impacts that have shaped Earth and other terrestrial planets. The giant planet has been both destroyer and protector, influencing the evolution of life on Earth in ways we are only beginning to understand. The outer solar system contains two planets called ice giants, Uranus and Neptune. The term ice giant distinguishes them from the gas giants Jupiter and Saturn, but the name can be misleading. These planets are not giant balls of frozen water ice. Rather, they are called ice giants because they contained large amounts of materials that were solid ices in the cold outer regions of the protoplanetary disk where they formed. In planetary science, the term ices refers to compounds that are solid at low temperatures, including water, methane, ammonia, and other volatile compounds. In the warm inner solar system, these compounds are gases, but in the cold outer solar system beyond the snowline, these compounds condensed into solid ices that accreted into the cores of forming planets. Uranus and Neptune have rocky cores surrounded by thick mantles composed of water, methane, and ammonia. These substances are not frozen solid, but exist under immense pressure in a hot, dense fluid state, sometimes called a superionic or exotic ice phase. Above this mantle lies a gaseous atmosphere of hydrogen, helium, and methane. The presence of methane in the upper atmospheres of Uranus and Neptune gives these planets their distinctive blue color. Methane absorbs red light, reflecting back primarily blue wavelengths. Neptune appears a deeper, richer blue than Uranus due to a currently unknown atmospheric component that enhances the absorption. Uranus is unique among planets in having its rotation axis tilted 98 degrees relative to its orbital plane. The planet essentially rolls along its orbit on its side. This extreme tilt likely resulted from one or more giant impacts early in the planet's history. The unusual orientation creates extreme seasonal variations, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness as Uranus orbits the Sun. Neptune, the outermost planet, was the first planet discovered through mathematical prediction rather than direct observation. Irregularities in Uranus's orbit led astronomers to hypothesize another planet beyond Uranus. Independent calculations by John Couch-Adams and Urbain Le Verrier predicted where the planet should be found. When observers turned telescopes to that location in 1846, they found Neptune almost exactly where predicted, a triumph of celestial mechanics. Our solar system is a laboratory for understanding planetary science, orbital mechanics, and fundamental physics. The Sun's core burns at 15 million degrees, sustaining fusion. Mercury's anomalous precession confirmed general relativity. Gravitational slingshots enable ambitious space missions. Lagrange points provide stable locations for satellites. Tidal locking explains why the moon shows one face. The Oberth effect makes rocket burns more efficient at high speeds. Solar sails demonstrate light's momentum. Saturn would float due to its low density. Jupiter shields Earth from some impacts. And ice giants contain exotic forms of water, methane, and ammonia. Each world in our solar system has its own character, its own story. Mercury, scorched and cratered, racing around the Sun. Venus, shrouded in thick clouds, a runaway greenhouse. Earth, the only world we know that harbors life. Mars, cold and dusty, perhaps once warmer and wetter. Jupiter, the giant, a world of storms and powerful radiation. Saturn, adorned with magnificent rings. Uranus, rolling on its side through its long seasons. Neptune, windswept and blue at the edge of the planetary realm. And beyond, the small worlds of the Kuiper Belt and distant Oort cloud, frozen relics of solar system formation. The universe operates according to inexorable laws that govern the flow of energy, the direction of time, and the ultimate fate of all things. These are the laws of thermodynamics, principles so fundamental that they apply to every system, from the smallest molecular interaction to the cosmos itself. They determine what is possible and what is forbidden, why time flows forward, and why the universe evolves in the direction it does. Tonight, we explore these profound laws and their implications for everything that exists. There are 4 laws of thermodynamics, numbered 0 through 3. The 0th law was formulated last, but describes the most fundamental concept, so it received the lowest number. Together, these laws form an unbreakable framework that constrains all physical processes. They have been tested countless times in countless ways and have never been violated. They are as close to absolute truth as science possesses. These laws apply universally. They govern the efficiency of engines, the direction of chemical reactions, the evolution of stars, the expansion of the universe, and the ultimate fate of everything. You cannot circumvent them with clever engineering or exotic materials. They are woven into the structure of reality itself. Understanding thermodynamics is understanding the deep rules by which the universe plays. The first law of thermodynamics is the principle of energy conservation. Energy cannot be created or destroyed, only transformed from one form to another. The total energy in an isolated system remains constant. This is sometimes colloquially expressed as you cannot win, meaning you cannot get more energy out of a system than you put in. Energy takes many forms. Kinetic energy is the energy of motion. Potential energy is stored energy due to position in a field, like gravitational or electromagnetic. Thermal energy is the random kinetic energy of atoms and molecules. Chemical energy is stored in the bonds between atoms. Nuclear energy is stored in the binding of atomic nuclei. Mass itself is a form of energy according to Einstein's equation. All these forms can be converted into each other, but the total remains constant. When you burn gasoline in a car engine, chemical energy in the fuel is converted to thermal energy through combustion. Some thermal energy is converted to mechanical energy, pushing pistons and turning wheels. Some is lost as heat through the exhaust and radiator. If you account for all forms of energy before and after, including the energy carried away as heat, exhaust gases, sound, and the kinetic energy of the moving car, the total is exactly the same. No energy has been created or destroyed, only transformed and redistributed. The conservation of energy has profound implications. Perpetual motion machines of the first kind, which would create energy from nothing, are impossible. Any device that claims to generate more energy than it consumes must be either fraudulent or misunderstood. The first law is absolute. Every legitimate power generation technology, from burning coal to nuclear fusion to solar panels, works by converting energy from one form to another, never creating it from nothing. Energy conservation also means that the total energy content of the universe is constant. Energy can flow between regions, converting between forms, but the sum never changes. If the universe is truly isolated, its total energy has been constant since the Big Bang and will remain constant forever. The second law of thermodynamics is more subtle and more profound. It states that the total entropy of an isolated system always increases over time or remains constant in ideal reversible processes. Entropy is a measure of disorder or randomness, the number of microscopic arrangements consistent with a system's macroscopic properties. The second law is often expressed as you cannot break even, meaning you cannot run a process without generating waste heat and increasing total entropy. Entropy gives time its direction. Most fundamental laws of physics are time reversible. The equations work equally well forward or backward in time. But the second law is not reversible. Entropy increases in one direction only, from past to future. This is the arrow of time. Broken eggs do not spontaneously reassemble. Heat flows from hot objects to cold objects, never the reverse. Mixed cream and coffee do not separate. All these everyday observations follow from the second law. At the microscopic level, entropy relates to probability. Systems naturally evolve towards states that can be realized in more ways, simply because those states are more likely. A gas confined to one corner of a room can be arranged in relatively few ways. The same gas spread throughout the room can be arranged in vastly more ways. Each individual molecule moves randomly, but collectively they spread out because the spread out state is overwhelmingly more probable. This is entropy increasing. The second law has profound implications. It explains why heat engines cannot be perfectly efficient. A perfect heat engine would convert thermal energy entirely into work without any waste heat. But this would decrease entropy, violating the second law. Every real engine must dump some waste heat into the environment, increasing the environment's entropy more than the engine's entropy decreases. The maximum theoretical efficiency of a heat engine depends only on the temperatures of the hot and cold reservoirs it operates between, as derived by Carnot in the 19th century. The second law explains why chemical reactions release heat, why friction generates warmth, why mixing increases disorder, and why useful energy inevitably degrades into unusable thermal energy. It predicts the eventual heat death of the universe. When all energy is evenly distributed, entropy is maximized, and no useful work can be done. The second law is the ultimate reason why perpetual motion machines of the second kind, which would decrease entropy without compensating increases elsewhere, are impossible. The third law of thermodynamics states that the entropy of a perfect crystal at absolute zero temperature is zero, and that absolute zero cannot be reached by any finite series of processes. You can get arbitrarily close to absolute zero, but you can never reach it exactly. This is sometimes stated as you cannot get out of the game, meaning you cannot escape thermodynamics by cooling to absolute zero. Absolute zero. 0 Kelvin or negative 273.15 degrees Celsius is the temperature at which classical thermal motion ceases. At absolute zero, a perfect crystal would have only one possible microscopic arrangement, the ground state, so its entropy would be zero. But real systems can never be cooled to exactly absolute zero. Each step of cooling requires removing thermal energy, which becomes progressively more difficult as temperature decreases. The lowest temperature ever achieved in a laboratory is a few billionths of a degree above absolute zero, reached using sophisticated laser cooling and evaporative cooling techniques applied to dilute gases of atoms. At such temperatures, quantum effects dominate, and atoms behave in strange collective ways. Forming Bose-Einstein condensates where thousands or millions of atoms occupy the same quantum state and act as a single quantum object. Even in the coldest regions of space, the temperature never reaches absolute zero. The cosmic microwave background provides a minimum temperature of about 2.7 Kelvin everywhere in the universe. To cool below this requires active refrigeration. The third law ensures that absolute zero remains an unreachable ideal, an asymptotic limit approached but never attained. Black holes present a puzzle for thermodynamics. They seem to violate the second law because anything falling into a black hole, including its entropy, disappears from the observable universe. If entropy can be destroyed by throwing it into a black hole, the second law would be violated. The resolution came from the work of Jacob Bekenstein and Stephen Hawking in the 1970s. Bekenstein proposed that black holes have entropy proportional to the area of their event horizon. As matter falls into a black hole, increasing its mass and the area of its horizon, the black hole's entropy increases by more than the entropy that fell in. Total entropy still increases, preserving the second law. Hawking's discovery of black hole radiation confirmed this picture. Black holes emit thermal radiation exactly as expected from thermodynamic objects with temperature and entropy. The formula for black hole entropy is remarkable. The entropy is proportional to the area of the event horizon measured in Planck units, not to the volume as you might expect. This suggests that information about what falls into a black hole is somehow encoded on its two-dimensional surface, rather than in its three-dimensional volume. This holographic principle has become a major theme in theoretical physics, suggesting that the information content of any region of space is limited by the area of its boundary, not its volume. Black hole thermodynamics bridges general relativity, quantum mechanics and thermodynamics, three pillars of modern physics. Understanding how these fit together remains one of the deepest challenges in theoretical physics. Black hole entropy is a clue that a quantum theory of gravity must incorporate thermodynamic principles at a fundamental level. The universe today is filled with structure. Galaxies cluster in filaments and walls surrounding vast voids. Stars form in nebulae. Planets orbit stars. Life arises on at least one planet. All this structure represents order, regions where entropy is locally low compared to maximum disorder. Yet the second law says entropy always increases. How can structure form if entropy increases? The resolution is that the universe began in an extraordinarily low entropy state. The Big Bang was not a hot, chaotic mess, but rather a remarkably smooth, uniform, ordered state. The early universe had extremely high energy density, but low entropy because it was nearly homogeneous. All regions were almost identical, giving it a very special, unlikely configuration. As the universe expanded and cooled, energy became available to do work, forming structure. While local regions like galaxies and stars have low entropy, their formation increased entropy elsewhere by larger amounts. Stars generate entropy by converting ordered nuclear energy into disordered thermal radiation. The overall entropy of the universe increases even as local pockets of order form. The low entropy initial state of the universe is a profound mystery. Why did the universe begin so ordered? The answer may lie in cosmic inflation or in deeper principles not yet understood. The initial low entropy provided the universe with vast reserves of order to spend. allowing complexity to arise. The entire history of the cosmos, from the Big Bang to heat death, is the story of entropy increasing from a very low initial value to a maximum final value. Every interesting process, from star formation to biological evolution to conscious thought, is powered by this entropy gradient. Structure and complexity arise as the universe explores the vast space of possible configurations on its journey toward maximum entropy. We exist because the universe started in an unlikely state and is still in the process of relaxing toward equilibrium. In 1867, James Clerk Maxwell proposed a thought experiment that seemed to violate the second law. Imagine a box of gas divided by a partition with a small door. A tiny intelligent being, called Maxwell's demon, controls the door. The demon observes individual molecules. When a fast molecule approaches from the left, the demon opens the door, allowing it to pass to the right. When a slow molecule approaches from the right, the demon opens the door, letting it pass to the left. Fast and slow molecules approaching from the wrong directions are blocked. Over time, the demon concentrates fast molecules on the right and slow molecules on the left. The right side becomes hot and the left side cold, creating a temperature difference from an initially uniform gas. This temperature difference could be used to run a heat engine and do work, seemingly violating the second law by decreasing entropy without compensating increases. The resolution came from understanding the connection between information and thermodynamics. The demon must observe molecules to decide when to open the door. Observation requires measurement, which requires interaction, which generates entropy. The demon must also store information about which molecules are where, filling its memory. Eventually, the demon's memory fills up and must be erased to continue operating. Erasing information necessarily increases entropy, as proved by Rolf Landauer. When you properly account for all entropy changes, including those associated with the demon's measurements, memory, and information processing, the second law is preserved. Maxwell's demon demonstrates deep connections between information, computation, and thermodynamics. Information is physical. Acquiring, storing, processing, and erasing information all have thermodynamic costs. These insights have become important in understanding the fundamental limits of computation and have led to new fields, studying the thermodynamics of information. What we perceive as temperature is actually a measure of the average kinetic energy of atoms and molecules. In a hot object, atoms vibrate rapidly. In a cold object, they vibrate slowly. Temperature is fundamentally motion at the microscopic scale. Heat is energy transferring from faster moving molecules to slower moving molecules through collisions. When you touch a hot stove, fast moving atoms in the metal collide with molecules in your skin, transferring kinetic energy. This energy propagates through your skin, exciting nerve endings, which send signals to your brain interpreting the sensation as heat. The metal cools slightly as it loses energy. Your skin warms as it gains energy. Eventually, thermal equilibrium is reached, where both have the same average molecular kinetic energy, meaning the same temperature. Different materials have different heat capacities, requiring different amounts of energy to change their temperature. Water has a high heat capacity, meaning it takes considerable energy to raise its temperature. Metals have lower heat capacities, heating and cooling quickly. This is why a metal spoon in hot soup feels hotter than the soup itself, even though they are at the same temperature. The metal conducts heat to your skin more efficiently. Temperature can be measured in several scales. Celsius and Fahrenheit are familiar but arbitrary scales based on the properties of water at Earth's atmospheric pressure. The Kelvin scale is fundamental, starting at absolute zero where molecular motion ceases. Temperature in Kelvin directly relates to average molecular kinetic energy. Understanding temperature as molecular motion explains gas laws, phase transitions, thermal expansion, and countless other phenomena. It unifies our macroscopic experience of heat with the microscopic reality of atomic motion. The seemingly smooth, continuous sensation of warmth emerges from the chaotic jostling of uncountable atoms. The second law says entropy increases meaning the universe evolves toward maximum disorder. But maximum disorder means all possible states are equally probable. Random quantum fluctuations can produce any configuration given enough time. In an infinite or very old universe, fluctuations could spontaneously assemble anything, including a conscious brain complete with false memories of a past that never happened. This Boltzmann brain paradox, named after Ludwig Boltzmann, who worried about similar ideas, suggests that in an infinite universe, it is vastly more probable for a single brain to randomly fluctuate into existence than for an entire ordered universe to exist with the history we observe. Yet we seem to observe an ordered universe, not a chaotic void with brief hallucinations. This creates a paradox. Why should we trust our observations and memories if it is more probable that we are Boltzmann brains with false memories? The paradox assumes the universe will exist eternally in a high entropy state with rare fluctuations. Modern cosmology suggests this may not be the case. The accelerating expansion driven by dark energy means distant regions become causally disconnected. The nature of vacuum energy in the far future remains uncertain. If the universe has a finite lifetime or finite volume accessible to fluctuations, Boltzmann brains may not be probable after all. The paradox highlights the strange implications of statistical mechanics and cosmology. It forces us to think carefully about probability, observation, and the nature of existence. Most physicists regard Boltzmann brains as a problem to be solved rather than a likely description of reality, using the paradox to constrain cosmological theories. Any theory that predicts Boltzmann brains are more common than normal observers is probably wrong. The zeroth law of thermodynamics, formulated after the others but given a lower number due to its fundamental nature, states that if system A is in thermal equilibrium with system C, and system B is also in thermal equilibrium with system C, then A and B are in thermal equilibrium with each other. This seems obvious but has profound implications. It allows us to define temperature consistently. Thermal equilibrium means no net heat flows between systems when they are in contact. The zeroth law says thermal equilibrium is transitive. This transitivity allows us to create thermometers. A thermometer reaches thermal equilibrium with an object being measured. If the thermometer shows the same reading for two different objects, those objects are at the same temperature and would be in thermal equilibrium with each other. Without the zeroth law, temperature would not be a well-defined property. You could have situations where object A is in equilibrium with B and B with C, but A and C are not in equilibrium with each other. This would make temperature meaningless. The zeroth law ensures that temperature is a state function, depending only on the current condition of a system, not on its history. The zeroth law underlies all of thermometry and establishes temperature as a fundamental thermodynamic variable. It may seem trivial, but it is essential for the logical consistency of thermodynamics. It is the foundation upon which the other laws rest. The laws of thermodynamics are universal, applying everywhere from molecular scales to the entire cosmos. The first law conserves energy in all processes. The second law increases entropy, giving time its direction and limiting efficiency. The third law makes absolute zero unattainable. Black holes possess entropy related to their surface area. The universe began in a low entropy state and evolves toward maximum disorder. Maxwell's demon connects information and thermodynamics. Temperature measures molecular kinetic energy. Boltzmann brains are improbable paradoxes, highlighting the strangeness of infinite time. The zeroth law defines temperature through thermal equilibrium. These laws are not mere guidelines, but absolute constraints on what is possible. They have been tested exhaustively and have never failed. They transcend specific theories, remaining valid even as our understanding of physics has revolutionized from classical to quantum to relativistic. Whatever the ultimate theory of everything may be, it must reduce to thermodynamics in appropriate limits. The laws of thermodynamics tell us that the universe has a history and a future. It began in an unlikely ordered state and inexorably evolves toward disorder. Complexity and structure arise temporarily as the universe explores the vast landscape of possible configurations, but ultimately, entropy increases, energy becomes evenly distributed, and activity ceases. This is not a failure, but a consequence of the most fundamental laws governing reality. As you rest tonight, reflect that your body is a thermodynamic system, maintaining low local entropy by consuming food and generating waste heat and entropy. Your metabolism is an engine burning fuel to do work, constrained by the same laws that govern stars and galaxies. Your thoughts and consciousness emerge from thermodynamic processes in your brain, neurons firing, chemicals flowing, energy transforming. You exist in temporary defiance of maximum entropy, a localized pocket of order maintained by constant energy flow. You are not separate from the universe, but part of it, subject to its laws, made of its matter, powered by its energy. The same principles that govern the evolution of galaxies govern the operation of your cells. The universe is running down, but it is not dying. It is exploring, transforming, becoming. From simplicity to complexity, and eventually back to simplicity, the cosmos follows its thermodynamic destiny. And in this brief middle epoch, when the universe is neither too young nor too old, structure flourishes, stars shine, planets orbit, and life emerges to contemplate the laws that govern everything. Sleep well in this thermodynamic universe. Where energy is conserved, entropy increases, absolute zero is unreachable, and temperature has meaning. Rest in the knowledge that the same laws apply everywhere, from the smallest atom to the largest galaxy, binding all of existence in a unified framework of astonishing elegance and power. Dream peacefully, temporary island of order in the entropic sea, knowing your place in the grand thermodynamic story of the cosmos.